Hello and welcome back. In this week, we're going to go over the basics of neural network programming. It turns out that when you implement a neural network, there are some implementation techniques that are going to be really important. For example, if you have a training set of M training examples, you might be used to processing the training set by having a for loop step through your M training examples. But it turns out that when you implement a neural network, you usually want to process your entire training set without using an explicit for loop to loop over your entire training set. So you'll see how to do that in this week's materials. Another idea, when you organize the computation of a neural network, usually you have what's called a forward pass or forward propagation step, followed by a backward pass or what's called a backward propagation step. And so in this week's materials, you also get an intuition about why the computations in learning in a neural network can be organized in this forward propagation and a separate backward propagation. For this week's materials, I want to convey these ideas using logistic regression in order to make the ideas easier to understand. But even if you've seen logistic regression before, I think that there'll be some new and interesting ideas for you to pick up in this week's materials. So with that, let's get started. Logistic regression is an algorithm for binary classification. So let's start by setting up the problem. Here's an example of a binary classification problem. You might have an input of an image like that and want to output a label to recognize this image as being either a cat, in which case you output 1, or non-cat, in which case you output 0. And we're going to use Y to denote the output label. Let's look at how an image is represented in a computer. To store an image, your computer stores 3 separate matrices corresponding to the red, green, and blue color channels of this image. So if your input image is 64 pixels by 64 pixels, then you would have 3 64 by 64 matrices corresponding to the red, green, and blue pixel intensity values for your image. Although to make these fit on the slide, I drew these as much smaller matrices. So these are actually 5 by 4 matrices rather than 64 by 64. So to turn these pixel intensity values into a feature vector, what we're going to do is unrow all of these pixel values into a input feature vector x. So to unrow all of these pixel intensity values into a feature vector, what we're going to do is define a feature vector x corresponding to this image as follows. We're just going to take all the pixel values, 255, 231, and so on, 255, 231, and so on, until we've listed all the red pixels, and then eventually 255, 134, 255, 134, and so on, until we get a very long feature vector listing out all the red, green, and blue pixel intensity values of this image. So if this image is a 64 by 64 image, the total dimension of this vector x will be 64 by 64 by 3, because that's the total numbers we have in all of these matrices, which in this case turns out to be 12288. That's what you get if you multiply out those numbers. And so we're going to use nx equals 12288 to represent the dimension of the input features x. And sometimes for brevity, I might also just use lowercase n to represent the dimension of this input feature vector. So in binary classification, our goal is to learn a classifier that can input an image represented by its feature vector x and predict whether the corresponding label y is 1 or 0. That is, whether this is a cat image or a non-cat image. Let's now lay out some of the notation that we'll use throughout the rest of this course. A single training example is represented by a pair x, y, where x is an nx dimensional feature vector, and y, the label, is either 0 or 1. Your training sets will comprise lowercase m training examples, and so your training sets will be written x1, y1, which is the input and output for your first training example, x2, y2 for your second training example, up to xm, ym, which is your last training example, and then that altogether is your entire training set. So I'm going to use lowercase m to denote the number of training examples, and sometimes to emphasize that this is the number of training examples, I might write this as m subscript train. And when we talk about a test set, we might sometimes use m subscript test to denote the number of test examples. So that's the number of test examples. Finally, to put all of the training examples into a more compact notation, we're going to define a matrix capital X as defined by taking your training set inputs, x1, x2, and so on, and stacking them in columns. So if you take x1 and put that as the first column of this matrix, and x2, put that as the second column, and so on, down to xm, then this is the matrix capital X. So this matrix X will have m columns, where m is the number of training examples, and the number of rows, or the height of this matrix, is nx. Notice that in other courses, you might see the matrix capital X defined by stacking up the training examples in rows, like so, x1 transpose down to xm transpose. But it turns out that when you're implementing neural networks, using this convention I have on the left will make the implementation much easier. So just to recap, X is a nx by m dimensional matrix, and when you implement this in Python, you see that x.shape, that's the Python command for finding the shape of a matrix, that this is an nx comma m. This just means it's an nx by m dimensional matrix. So that's how you group the training examples input x into a matrix. How about the output labels y? It turns out that to make your implementation of a neural network easier, it will be convenient to also stack y in columns. So we're going to define capital Y to be equal to y1, y2, up to ym, like so. So y here will be a 1 by m dimensional matrix. And again, to use the Python notation, the shape of y will be 1 comma m, which just means this is a 1 by m matrix. And as you implement your neural network later in this course, you find that a useful convention will be to take the data associated with different training examples, and by data I mean either x or y or other quantities you see later, but to take the stuff or the data associated with different training examples and to stack them in different columns, like we've done here for both x and y. So that's the notation we'll use for logistic regression and for neural networks later in this course. If you ever forget what a piece of notation means, like what is m or what is n or what is something else, we've also posted on the course website a notation guide that you can use to quickly look up what any particular piece of notation means. So with that, let's go on to the next video where we'll start to flesh out logistic regression using this notation. In this video, we'll go over logistic regression. This is a learning algorithm that you use when the output labels y in a supervised learning problem are all either 0 or 1, so for binary classification problems. Given an input feature vector x may be corresponding to an image that you want to recognize as either a cat picture or not a cat picture, you want an algorithm that can output a prediction, which we call y hat, which is your estimate of y. More formally, you want y hat to be the probability or the chance that y is equal to 1 given the input features x. So in other words, if x is a picture, as we saw in the last video, you want y hat to tell you what is the chance that this is a cat picture. So x, as we said in the previous video, is a nx dimensional vector. Given that, the parameters of logistic regression will be w, which is also an nx dimensional vector, together with b, which is just a real number. So given an input x and the parameters w and b, how do we generate the output y hat? Well, one thing you could try that doesn't work would be to have y hat be w transpose x plus b, kind of a linear function of the input x. And in fact, this is what you use if you were doing linear regression. But this isn't a very good algorithm for binary classification because you want y hat to be the chance that y is equal to 1. So y hat should really be between 0 and 1. And it's difficult to enforce that because W transpose X plus B can be much bigger than 1 or it can even be negative, which doesn't make sense for a probability that you want to be between 0 and 1. So in logistic regression, our output is instead going to be y hat equals the sigmoid function applied to this quantity. This is what the sigmoid function looks like. If on the horizontal axis I plot z, then the function sigmoid of z looks like this. So it goes smoothly from 0 up to 1. Let me label my axes here. This is 0. And it crosses the vertical axis at 0.5. So this is what sigmoid of z looks like, and we're going to use z to denote this quantity W transpose X plus B. Here's the formula for the sigmoid function. Sigmoid of z, where z is a real number, is 1 over 1 plus e to the negative z. So notice a couple things. If z is very large, then e to the negative z will be close to 0, so then sigmoid of z will be approximately 1 over 1 plus something very close to 0, because e to the negative of a very large number will be close to 0, so this is close to 1. And indeed, if you look on the plot on the left, if z is very large, then sigmoid of z is very close to 1. Conversely, if z is very small, or if it's a very large negative number, then sigmoid of z becomes 1 over 1 plus e to the negative z, and this becomes e to a huge number, so this becomes, think of it as 1 over 1 plus a number that is very, very big. And so that's close to 0. And indeed, you see that as z becomes a very large negative number, sigmoid of z, goes very close to 0. So when you implement logistic regression, your job is to try to learn parameters w and b so that y hat becomes a good estimate of the chance of y being equal to 1. Before moving on, just another note on the notation. When we program neural networks, we'll usually keep the parameter w and the parameter b separate, where here b corresponds to an intercept term. In some other classes, you might have seen a notation that handles this differently. In some conventions, you define an extra feature called x0 and make that equal to 1, so that now x is in R of nx plus 1, and then you define y hat to be equal to sigma of theta transpose x. In this alternative notational convention, you have vector parameters theta, theta 0, theta 1, theta 2, down to theta and x. And so theta 0 plays a role of b, that's just a real number, and theta 1 down to theta nx play the role of w. It turns out when you implement your neural network, it'll be easier to just keep b and w as separate parameters. And so in this class, we will not use any of this notational convention that I just wrote in red. If you've not seen this notation before in other classes, don't worry about it. It's just that for those of you that have seen this notation, I wanted to mention explicitly that we're not using that notation in this course. But if you've not seen this before, it's not important and you don't need to worry about it. So you've now seen what the logistic regression model looks like. Next, to train the parameters w and b, you need to define a cost function. Let's do that in the next video. In the previous video, you saw the logistic regression model. To train the parameters w and b of your logistic regression model, you need to define a cost function. Let's take a look at a cost function you can use to train logistic regression. To recap, this is what we had defined from the previous slide. So your output y hat is sigmoid of w transpose x plus b, where sigmoid of z is as defined here. So to learn parameters for your model, you're given a training set of m training examples, and it seems natural that you want to find parameters W and B so that at least on the training set, the outputs you have, the predictions you have on the training set, which I'm going to write as y hat I, that will be close to the ground truth labels yi that you got in the training set. So to fill in a little bit more detail for the equation on top, we had said that y hat is as defined at the top for a training example x, and of course for each training example we're using these superscripts with round brackets with parentheses to index into different training examples. Your prediction on training example I, which is y hat I, is going to be obtained by taking the sigmoid function and applying it to W transpose xi, the input for the training example, plus b. And you can also define zi as follows, where zi is equal to W transpose xi plus b. So throughout this course, we're going to use this notational convention that the superscript parentheses I refers to data, be it x or y or z or something else, associated with the ith training example, associated with the ith example. Okay, that's what the superscript I in parentheses means. Now let's see what loss function or an error function we can use to measure how well our algorithm is doing. One thing you could do is define the loss when your algorithm outputs y hat and the true label as y to be maybe the squared error or 1/2 a squared error. It turns out that you could do this, but in logistic regression, people don't usually do this because when you come to learn the parameters, you find that the optimization problem, which we'll talk about later, becomes non-convex. So you end up with an optimization problem with multiple local optima. So gradient descent may not find the global optimum. If you didn't understand the last couple of comments, don't worry about it. We'll get to it in a later video. But the intuition to take away is that this function L, called the loss function, is a function we'll need to define to measure how good our output y hat is when the true label is y. And squared error seems like it might be a reasonable choice, except that it makes gradient descent not work well. So in logistic regression, we will actually define a different loss function that plays a similar role as squared error, but will give us an optimization problem that is convex, and so we'll see in a later video becomes much easier to optimize. So what we use in logistic regression is actually the following loss function, which I'm just going to write out here, is negative y log y hat plus 1 minus y log 1 minus y hat. Here's some intuition for why this loss function makes sense. Keep in mind that if we're using squared error, then you want this squared error to be as small as possible. And with this logistic regression loss function, we'll also want this to be as small as possible. To understand why this makes sense, let's look at the two cases. In the first case, let's say y is equal to 1, then the loss function y hat comma y is just this first term, right? And there's a negative sign, so it's negative log y hat if y is equal to 1, because if y equals 1, then the second term 1 minus y is equal to 0. So this says if y equals 1, you want negative log y hat to be as small as possible. So that means you want log y hat to be large, to be as big as possible, and that means you want y hat to be large. But because y hat is this sigmoid function, it can never be bigger than 1. So this is saying that if y is equal to 1, you want y hat to be as big as possible, but it can't ever be bigger than 1. So it's saying you want y hat to be close to 1 as well. The other case is if y equals 0. If y equals 0, then this first term in the loss function is equal to 0 because y, 0. And then the second term defines the loss function. So the loss becomes negative log 1 minus y hat. And so if in your learning procedure you try to make the loss function small, what this means is that you want log 1 minus y hat to be large, and because there's a negative sign there. And then through a similar piece of reasoning, you can conclude that this loss function is trying to make y hat as small as possible. And again, because y hat has to be between 0 and 1, this is saying that if y is equal to 0, then your loss function will push the parameters to make y hat as close to 0 as possible. Now, there are a lot of functions with roughly this effect, that if y is equal to 1, it will try to make y hat large, and if y is equal to 0, it will try to make y hat small. We just gave here in green a somewhat informal justification for this particular loss function. We'll provide an optional video later to give a more formal justification for why in logistic regression we like to use the loss function with this particular form. Finally, the loss function was defined with respect to a single training example. It measures how well you're doing on a single training example. I'm now going to define something called the cost function, which measures how well you're doing on the entire training set. So the cost function, j, which is applied to your parameters w and b, is going to be the average, really, 1 over m of the sum of the loss function applied to each of the training examples in turn, where here y hat is of course the prediction output by your logistic regression algorithm using a particular set of parameters w and b. And so just to expand this out, this is equal to negative 1 over m sum from I equals 1 through m of the definition of the loss function above. So this is yi log y hat I plus 1 minus yi log 1 minus y hat I. I guess I can put square brackets here. So the minus sign is outside everything else. So the terminology I'm going to use is that the loss function is applied to just a single training example, like so, and the cost function is the cost of your parameters. So in training your logistic regression model, we're going to try to find parameters w and b that minimize the overall cost function j written at the bottom. So you've just seen the setup for the logistic regression algorithm, the loss function for a training example, and the overall cost function for the parameters of your algorithm. It turns out that logistic regression can be viewed as a very, very small neural network. In the next video, we'll go over that so you can start gaining intuition about what neural networks do. So with that, let's go on to the next video about how to view logistic regression as a very small neural network. You've seen the logistic regression model. You've seen the loss function that measures how well you're doing on a single training example. You've also seen the cost function that measures how well your parameters w and b are doing on your entire training set. Now, let's talk about how you can use the gradient descent algorithm to train or to learn the parameters w on your training set. To recap, here is the familiar logistic regression algorithm, and we have on the second line the cost function j, which is a function of your parameters w and b, and that's defined as the average, so it's 1 over m times the sum of this loss function. And so the loss function measures how well your algorithm's outputs y hat I on each of the training examples stacks up or compares to the ground truth label yi on each of the training examples. And the full formula is expanded out on the right. So the cost function measures how well your parameters w and b are doing on the training set. So in order to learn a set of parameters w and b, it seems natural that we want to find w and b that make the cost function j of w comma b as small as possible. So here's an illustration of gradient descent. In this diagram, the horizontal axes represent your space of parameters w and b. In practice, w can be much higher dimensional, but for the purposes of plotting, let's illustrate w as a single real number and b as a single real number. The cost function j of wb is then some surface above these horizontal axes w and b. So the height of this surface represents the value of j comma b at a certain point. And what we want to do is really to find the value of w and b that corresponds to the minimum of the cost function j. It turns out that this particular cost function j is a convex function, so it's just a single big bow, so this is a convex function, and this is as opposed to functions that look like this, which are non-convex and has lots of different local optima. So the fact that our cost function j of wb as defined here is convex is one of the huge reasons why we use this particular cost function j for logistic regression. So to find a good value for the parameters, what we'll do is initialize w and b to some initial value, maybe denoted by that little red dot. And for logistic regression, almost any initialization method works. Usually you initialize the values to 0. Random initialization also works, but people don't usually do that for logistic regression. But because this function is convex, no matter where you initialize, you should get to the same point, or roughly the same point. And what gradient descent does is it starts at that initial point and then takes a step in the steepest downhill direction. So after one step of gradient descent, you might end up there, because it's trying to take a step downhill in the direction of steepest descent, or as quickly downhill as possible. So that's one iteration of gradient descent. And after 2 iterations of gradient descent, you might step there, 3 iterations, and so on. I guess this is now hidden by the back of the plot until eventually, hopefully you converge to this global optimum, or get to something close to the global optimum. So this picture illustrates the gradient descent algorithm. Let's write out a bit more of the details. For the purpose of illustration, let's say that there's some function j of w that you want to minimize, and maybe that function looks like this. To make this easier to draw, I'm going to ignore b for now, just to make this a one-dimensional plot instead of a higher-dimensional plot. So gradient descent does this. We're going to repeatedly carry out the following update. I'm going to take the value of w and update it. I'm going to use colon equals to represent updating w. So set w to w minus alpha times, and this is a derivative, d of jw dw. And we'll repeatedly do that until the algorithm converges. So a couple points in the notation. Alpha here is the learning rate and controls how big a step we take on each iteration of gradient descent. We'll talk later about some ways for choosing the learning rate alpha. And second, this quantity here, this is a derivative. This is basically the update or the change you want to make to the parameters w. When we start to write code to implement gradient descent, we're going to use the convention that the variable name in our code dw will be used to represent this derivative term. So when you write code, you write something like w equals, or colon equals, w minus alpha times dw. So we use dw to be the variable name to represent this derivative term. Now let's just make sure that this gradient descent update makes sense. Let's say that w was over here, so you're at this point on the cost function j of w. Remember that the definition of a derivative is the slope of a function at the point. So the slope of a function is really, the height divided by the width, right, of a little triangle here, this tangent to j of w at that point. And so here, the derivative is positive. W gets updated as w minus a learning rate times the derivative. The derivative is positive, and so you end up subtracting from w. So you end up taking a step to the left. And so gradient descent would make your algorithm slowly decrease the parameter if you had started off with this large value of w. As another example, if w was over here, then at this point, the slope here, or dj dw, will be negative, and so the gradient descent update would subtract alpha times a negative number, and so end up slowly increasing w. So you end up making w bigger and bigger with successive iterations of gradient descent, so that hopefully, whether you initialize on the left or on the right, gradient descent will move you towards this global minimum here. If you're not familiar with derivatives or with calculus and what this term dj of w dw means, don't worry too much about it. We'll talk some more about derivatives in the next video. If you have a deep knowledge of calculus, you might be able to have a deeper intuitions about how neural networks work. But even if you're not that familiar with calculus, in the next few videos we'll give you enough intuitions about derivatives and about calculus that you'll be able to effectively use neural networks. But the overall intuition for now is that this term represents the slope of the function. And we want to know the slope of the function at the current setting of the parameters so that we can take these steps of steepest descent, so that we know what direction to step in order to go downhill on the cost function j. So we wrote our gradient descent for j of w if only w was your parameter. In logistic regression, your cost function is a function of both w and b. So in that case, the inner loop of gradient descent, that is this thing here, the thing you have to repeat, becomes as follows. You end up updating w as w minus the learning rate times the derivative of j of wb with respect to w, and you update b as b minus the learning rate times the derivative of the cost function with respect to b. So these two equations at the bottom are the actual update you implement. As an aside, I just want to mention one notational convention in calculus that is a bit confusing to some people. I don't think it's super important that you understand calculus, but in case you see this, I want to make sure that you don't think too much of this, which is that in calculus, this term here, we actually write as follows with that funny squiggle symbol. So this symbol, this is actually just a lowercase d in a fancy font, in a stylized font. But when you see this expression, all this means is this is the derivative of j of w comma b, or really the slope of the function j of w comma b, how much that function slopes in the w direction. And the rule of the notation in calculus, which I think isn't totally logical, but the rule in the notation for calculus, which I think just makes things much more complicated than they need to be, is that if j is a function of two or more variables, then instead of using lowercase d, you use this funny symbol. This is called a partial derivative symbol. But don't worry about this. And if j is a function of only one variable, then you use lowercase d. So the only difference between whether you use this funny partial derivative symbol or lowercase d as we did on top is whether j is a function of two or more variables, in which case you use this symbol, the partial derivative symbol, or if j is only a function of one variable, then you use lowercase d. This is one of those funny rules of notation in calculus that I think just make things more complicated than they need to be. But if you see this partial derivative symbol, all it means is you're measuring the slope of the function with respect to one of the variables. And similarly, to adhere to the formally correct mathematical notation in calculus, because here j has two inputs, not just one, this thing at the bottom should be written with this partial derivative symbol. But it really means the same thing as, almost the same thing as lowercase d. Finally, when you implement this in code, we're going to use the convention that this quantity, really the amount by which you update w, will denote as the variable dw in your code. And this quantity, right, the amount by which you want to update b, will denote via the variable db in your code. Alright, so that's how you can implement gradient descent. Now, if you haven't seen calculus for a few years, I know that might seem like a lot more derivatives in calculus than you might be comfortable with so far. But if you're feeling that way, don't worry about it. In the next video, we'll give you better intuition about derivatives. And even without a deep mathematical understanding of calculus, with just an intuitive understanding of calculus, you will be able to make neural networks work effectively. So with that, let's go on to the next video where we'll talk a little bit more about derivatives. In this video, I want to help you gain an intuitive understanding of calculus and of derivatives. Now, maybe you're thinking that you haven't seen calculus since your college days, and depending on when you graduated, maybe that was quite some time back. Now, if that's what you're thinking, don't worry. You don't need a deep understanding of calculus in order to apply neural networks and deep learning very effectively. So if you're watching this video or some of the later videos and you're wondering, wow, is this stuff really for me? This calculus looks really complicated. My advice to you is the following, which is that watch the videos, and then if you could do the homework and complete the programming homework successfully, then you can apply deep learning. In fact, what you see later is that in week 4, we'll define a couple of types of functions that will enable enable you to encapsulate everything that needs to be done with respect to calculus. There are these functions called forward functions and backward functions that you learn about that lets you put everything you need to know about calculus into these functions so that you don't need to worry about them anymore beyond that. But I thought that in this foray into deep learning, that this week we should open up the box and peer a little bit further into the details of calculus. But really all you need is an intuitive understanding of this in order to build and successfully apply these algorithms. Oh, and finally, if you are among that maybe smaller group of people that are experts in calculus, if you're very familiar with calculus or derivatives, it's probably okay for you to skip this video. But for everyone else, let's dive in and try to gain an intuitive understanding of derivatives. I've plotted here the function f of a equals 3a, so it's just a straight line. To gain intuition about derivatives, let's look at a few points on this function. Let's say that a is equal to 2. In that case, f of a, which is equal to 3 times a, is equal to 6. So if a is equal to 2, then f of a will be equal to 6. Let's say we give the value of a, just a little bit of a nudge. I'm going to just bump up a little bit, so that is now 2.001, right? So I'm going to give a like a tiny little nudge to the right. So now is, let's say, 2.001. And this plot isn't to scale. 2.001, the 0.001 difference is too small to show in this plot. Just give a little nudge to the right. Now, f of a is equal to 3 times that, so 6.003. So plot this over here. This is not to scale. This is 6.003. So if you look at this little triangle here that I'm highlighting in green, what we see is that if I nudge a 0.001 to the right, then f of a goes up by 0.003. The amount that f of a went up is 3 times as big as the amount that I nudged a to the right. So we're going to say that the slope, or the derivative, of the function f of a at a equals 2, or when a is equals 2, that the slope is 3. And the term derivative basically means slope. It's just that derivative sounds like a scarier, more intimidating word, whereas slope is a friendlier way to describe the concept of derivative. So whenever you hear derivative, just think slope of the function. And more formally, the slope is defined as the height divided by the width of this little triangle that we have in green. So this is 0.003 over 0.001, and the fact that the slope is equal to 3, or the derivative is equal to 3, just represents the fact that when you nudge a to the right by 0.001 by a tiny amount, the amount that f of a goes up is 3 times as big as the amount that you nudged a in the horizontal direction. So that's all that the slope of a line is. Now let's look at this function at a different point. Let's say that a is now equal to 5. In that case, f of a, 3 times a, is equal to 15. So let's say I again give a nudge to the right. A tiny little nudge, so it's now bumped up to 5.001. F of a is 3 times that, so f of a is equal to 15.003. And so once again, when I bump a to the right, nudge a to the right by 0.001, f of a goes up 3 times as much. So the slope, again, at a equals 5, is also 3. So the way we write this, that the slope of the function f is equal to 3, we say d f of a dA, and this just means the slope of the function f of a, when you nudge the variable a tiny little amount, this is equal to 3. And an alternative way to write this derivative formula is as follows. You can also write this as d dA of f of a. So whether you put the f of a on top or whether you write it, down here, it doesn't matter. But all this equation means is that if I nudge a to the right a little bit, I expect f of a to go up by 3 times as much as I nudged the value of little a. Now, for this video, I explained derivatives talking about what happens if we nudge the variable a by 0.001. If you want the formal mathematical definition of derivatives, derivatives are defined with an even smaller value of how much you nudge a to the right. So it's not 0.001, it's not 0.00001, it's not 0.00000, and so on 1. It's sort of even smaller than that. And the formal definition of a derivative says whatever you nudge a to the right by an infinitesimal amount, basically an infinitely tiny amount. If you do that, does f of a go up 3 times as much as whatever was the tiny amount that you nudged a to the right. So that's actually the formal definition of a derivative. But for the purposes of our intuitive understanding, we're just going to talk about nudging a to the right by this small amount, 0.001. Even if it's 0.001 isn't exactly, tiny infinitesimal. Now, one property of the derivative is that no matter where you take the slope of this function, it is equal to 3. Whether a is equal to 2 or a is equal to 5, the slope of this function is equal to 3. Meaning that whatever is the value of a, if you increase it by 0.001, the value of f of a goes up by 3 times as much. So this function has the same slope everywhere. And one way to see that is that wherever you draw this little triangle, right, the height divided by the width always has a ratio of 3 to 1. So I hope this gives you a sense of what the slope or the derivative of a function means for a straight line, where in this example, the slope of the function was 3 everywhere. In the next video, let's take a look at a slightly more complex example where the slope of the function can be different at different points on the function. In this video, I want to show you a slightly more complex example where the slope of the function can be different at different points of the function. Let's start with an example. Here I plotted the function f of a equals a squared. Let's again look at the point a equals 2. So a squared, or f of a, is equal to 4. Let's nudge a slightly to the right. So now a is equal to 2.001. F of a, which is a squared, is going to be approximately 4.004. It turns out that the exact value, if you pull out a calculator and figure this out, is actually 4.004001. But I'm just going to say 4.004 is close enough. So what this means is that when a is equal to 2, let's draw this on the plot. So what we're saying is that if a is equal to 2, then f of a is equal to 4. And here the x and y axes are not drawn to scale. Technically, this vertical height should be much higher than this horizontal height. So the x and y axes are not on the same scale. But if I now nudge a to 2.001, then f of a becomes roughly 4.004. So if you draw this little triangle again, what this means is that if I nudge a to the right by 0.001, f of a goes up 4 times as much, by 0.004. So in the language of calculus, we say that the slope, that is the derivative of f of a at a equals 2 is 4. Or, to write this out with our calculus notation, we say that dda of f of a is equal to 4 when a is equal to 2. Now, one thing about this function f of a equals a squared is that the slope is different for different values of a. This is different than the example we saw on the previous slide. So let's look at a different point. If a is equal to 5, so instead of a equals 2, we now have a equals 5, then a squared is equal to 25. So that's f of a. If I nudge a to the right again, it's a tiny little nudge to a. So now a is 5.001, then f of a will be approximately 25.010. So what we see is that by nudging a up by 0.001, f of a goes up 10 times as much. So we have that dda f of a is equal to 10 when a is equal to 5, because f of a goes up 10 times as much as a does when I make a tiny little nudge to a. So one way to see why the derivative is different at different points is that if you draw that little triangle, right, at different locations on this, you see that the ratio of the height of the triangle over the width of the triangle is very different at different points on the curve. So here, the slope is equal to 4 when a is equal to 2, but it's equal to 10 when a is equal to 5. Now, if you pull up a calculus textbook will tell you that dda of f of a, so f of a is equal to a squared, so that's dda of a squared. One of the formulas you find in the calculus textbook is that this thing, the slope of the function a squared, is equal to 2a. I'm not going to prove this, but the way you find this out is that you open up a calculus textbook to the table of formulas, and it'll tell you the derivative of a squared is equal to 2a. And indeed, this is consistent with what we've worked out. Namely, when a is equal to 2, the slope of the function 2a is 2 times 2 is therefore equal to 4. And when a is equal to 5, then the slope of the function 2 times a is 2 times 5 is equal to 10. So if you ever pull up a calculus textbook and you see this formula, that the derivative of a squared is equal to 2a, all that means is that for any given value of a, if you nudge it upward by 0.001, already a tiny little value, you would expect f of a to go up by 2a. That is the slope or the derivative times however much you had nudged to the right the value of a. Now, one tiny little detail, I had used these approximate symbols here, and this wasn't exactly 4.004. There's an extra 0.001 hanging out there. It turns out that this extra 0.001, this little thing here, is because we were nudging a to the right by 0.001. If we're instead nudging it to the right by this infinitesimally small value, then this extra error term will go away. And you find that the amount that f of a goes up is exactly equal to the derivative times the amount that you nudge a to the right. And the reason why it's not 4.004 exactly is because derivatives are defined using these infinitesimally small nudges to a rather than 0.001, which is not, while 0.001 is small, is not infinitesimally small. So that's why the amount that f of a went up isn't exactly given by the formula, but is only kind of approximately given by the derivative. To wrap up this video, let's just go through a few more quick examples. The example you've already seen is that if f of a equals a squared, then the calculus textbook's formula table will tell you that the derivative is equal to 2a. And so the example we went through was that if a is equal to 2, f of a equals 4. And if we nudge a so it's a little bit bigger, then f of a is about 4.004. And so f of a went up 4 times as much. And indeed, when a is equal to 2, the derivative is equal to 4. Let's look at some other examples. Let's say instead that f of a is equal to a cubed. If you go to a calculus textbook and look up the table of formulas, you see that the slope of this function, again, the derivative of this function, is equal to 3a squared. So you can get this formula out of a calculus textbook. So what this means, so the way to interpret this is as follows. Let's take a equals 2 as an example again. So f of a, or a cubed, is equal to 8. Right? That's 2 to the power 3. So if we give a tiny little nudge, you find that f of a is about 8.012. And feel free to check this. Take 2.001 to the power of 3, you find that it's very close to 8.012. And indeed, when a is equal to 2, that's 3 times 2 squared. That's equal to 3 times 4, which is equal to 12. So the derivative formula predicts that if you nudge a to the right by a tiny little bit, f of a should go up 12 times as much. And indeed, this is true. When a went up by 0.001, f of a went up 12 times as much by 0.012. Just one last example, and then we'll wrap up. Let's say that f of a is equal to the log function, right? So I'm going to write log of a, and I'm going to use this as the base e logarithm. So some people write that as ln of a. So if you go to a calculus textbook, you find that when you take the derivative of log of a, right, so this is a function that I guess looks like that. The slope of this function is given by 1 over a. So the way to interpret this is that if a is any value, and again, let's just keep using a equals 2 as an example, and you nudge a to the right by 0.001, you would expect f of a to go up by 1 over a, that is by the derivative, times the amount that you increased a. So in fact, if you pull up a calculator, you find that if a is equal to 2, f of a is about 0.69315. And if you increase f, and if you increase a to 2.001, then f of a is about 0.69365. So it's gone up by 0.0005. And indeed, if you look at the formula for the derivative, when a is equal to 2, d dA f of a is equal to 1/2. So this derivative formula predicts that if you bump up a by 0.001, you would expect f of a to go up by only 1/2 as much, and 1/2 of 0.001 is 0.0005, which is exactly what we got, right? That when a goes up by 0.001, going from a equals 2 to a equals 2.001, f of a goes up by half as much. So it ends up going up by approximately 0.0005. So if you draw that little triangle, if you will, is that if on the horizontal axis this goes up by 0.001, on the vertical axis log of a goes up by half of that, so 0.0005. And so that 1 over a, or 1/2 in this case, when a is equal to 2, that's just the slope of this line when a is equal to 2. So that's it for derivatives. There are just two take-home messages from this video. First is that the derivative of a function just means the slope of a function. And the slope of a function can be different at different points on the function. In our first example, where f of a equals 3a, that was a straight line, the derivative was the same everywhere. It was 3 everywhere. But for other functions like f of a equals a squared or f of a equals log of a, the slope of the line varies. And so the slope or the derivative can be different at different points on the curve. So that's the first takeaway. Derivative just means slope of a line. Second takeaway is that if you want to look up the derivative of a function, you can flip open your calculus textbook or look up Wikipedia and often get a formula for the slope of these functions at different points. So that, I hope you have an intuitive understanding of derivatives or of slopes of lines. Let's go on to the next video. We'll start to talk about the computation graph and how to use that to compute derivatives of more complex functions. You've heard me say that the computations of a neural network are organized in terms of a forward pass or a forward propagation step in which we compute the output of the neural network, followed by a backward pass or a back propagation step which we use to compute gradients or compute derivatives. The computation graph explains why it is organized this way. In this video, we'll go through an example. In order to illustrate the computation graph, let's use a simpler example than logistic regression or a full-blown neural network. But let's say that we're trying to compute a function, j, which is a function of 3 variables a, b, and c. And let's say that function is 3 times a plus b times c. Computing this function actually has 3 distinct steps. The first is you need to compute what is b times c, and let's say we store that in a variable called u, so u is equal to b times c, and then you might compute v, which is equal to a times u, so let's say this is v, and then finally your output j is 3 times v, so this is your final function j that you're trying to compute. We can take these 3 steps and draw them in a computation graph as follows. Let's say I draw your 3 variables a, b, and c here. So the first thing we did was compute u equals b times c. So I'm going to put a rectangular box around that, and so the inputs to that are b and c. And then you might have v equals a plus u. So the inputs to that are v. So the inputs to that are u, which we just computed together with a. And then finally we have j equals 3 times b. So as a concrete example, if a equals 5, b equals 3, and c equals 2, then u equals bc would be 6, v equals a plus u would be 5 plus 6 is 11, j is 3 times that, so j is equal to 33. And indeed, hopefully you can verify that, this is 3 times 5 plus 3 times 2, and if you expand that out, you actually get 33 as the value of j. So the computation graph comes in handy when there is some distinguished or some special output variable, such as j in this case, that you want to optimize. And in the case of a logistic regression, j is of course the cost function that we're trying to minimize. And what we're seeing in this little example is that through a left to right pass, you can compute the value of j. And what we'll see in the next couple slides is that in order to compute derivatives, it will be a right to left pass like this, kind of going in the opposite direction as the blue arrows. That would be most natural for computing the derivatives. So to recap, the computation graph organizes the computation with this blue arrow left to right computation. Let's defer to the next video how you can do the backward red arrow right to left computation of the derivatives. Let's go on to the next video. In the last video, we worked through an example of using a computation graph to compute a function j. Now let's take a cleaned up version of that computation graph and show how you can use it to figure out derivative calculations for that function j. So here's our computation graph. Let's say you want to compute the derivative of j with respect to v. So what is that? Well, this says if we were to take this value of v and change it a little bit, how would the value of j change? Well, j is defined as 3 times v, and right now v is equal to 11. So if we were to bump up v by a little bit to 11.001, then j, which is 3v, so currently 33, will get bumped up to 33.003. So here we've increased v by 0.001, and the net result of that is that j goes up 3 times as much. So the derivative of j with respect to v is equal to 3, because the increase in j is 3 times the increase in v. And in fact, this is very analogous to the example we had in the previous video, where we had f of a equals 3a, and so we then derived that df dA, which with slightly simplified, a slightly sloppy notation, you can write as df dA was equal to 3, right? So instead, here we have j equals 3v, and so dj dv is equal to 3, with here j playing the role of f and v playing the role of a in this previous example that we had, right, from an earlier video. So in the terminology of backpropagation, what we're seeing is that if you want to compute the derivative of this final output variable, which usually is the variable you care most about, with respect to v, then we've done, sort of one step of backpropagation. So we've gone one step backwards in this graph. Now let's look at another example. What is dj dA? In other words, if we bump up the value of a, how does that affect the value of j? Well, let's go through the example. Right now a is equal to 5. So let's bump it up to 5.001. The net impact of that is that v, which was a plus u, so that was previously 11. This would get increased to 11.001. And then we've already seen as above that j now gets bumped up to 33.003. So what we're seeing is that if you increase a by 0.001, j increases by 0.003. And by increase a, I mean, if you were to take this value 5 and just plug in a new value, right, then the change to a will propagate to the right of the computation graph so that j ends up being 33.003. And so the increase to j is 3 times the increase to a, so that means this derivative is equal to 3. And one way to break this down is to say that if you change a, then that would change v, and through changing v, that would change j. And so the net change to the value of j, when you bump up the value, when you nudge the value of a up a little bit, is that first, by changing a, you end up increasing v. Well, how much does v increase, right? It'll increase by an amount that's determined by dv dA. And then the change in v will cause the value of j to also increase. So in calculus, this is actually called the chain rule, that if A affects V affects J, then the amount that J changes when you nudge A is the product of how much V changes when you nudge A times how much J changes when you nudge V. So in calculus, again, this is called the chain rule. And what we saw from this calculation is that if you increase A by 0.001, V changes by the same amount. So dV dA is equal to 1. So in fact, if you plug in what we have worked out previously, dV dJ is equal to 3, and dV dA is equal to 1. So the product of these 3 times 1, that actually gives you the correct value, that dJ dA is equal to 3. So this little illustration shows how by having computed dJ dV as its derivative with respect to this variable, it can then help you to compute dJ dA. And so that's another step of this backward calculation. I just want to introduce one more new notational convention, which is that when you're writing code to implement backpropagation, there'll usually be some final output variable that you really care about, right? So final output variable that you really care about or that you want to optimize. And in this case, this final output variable is J, is really the last node in your computation graph. And so a lot of the computations will be trying to compute the derivative of that, final output variable. So D of this final output variable with respect to some other variable. Let me just call that d var, right? So a lot of the computations you have will be to compute the derivative of the final output variable, really J in this case, with various intermediate variables such as A, B, C, U, or V. And when you implement this in software, what do you call this variable name, right? One thing you could do is in Python, you could write, give us a very long variable name, like d final output var over d var. But that's a very long variable name. You could call this, I guess, dj dvar. But because you're always taking derivatives with respect to dj, with respect to this final output variable, I'm going to introduce a new notation where in code, when you're computing this thing, in the code you write, we're just going to use the variable name dvar in order to represent that quantity. Okay, so dvar in the code you write will represent the derivative of the final output variable you care about, such as j, or sometimes the loss L, with respect to the various intermediate quantities you're computing in your code. So this thing here in your code, you use dv to denote this value. So dv would be equal to 3. And in your code, you represent this as a dA, right? Which is, we also figured out to be equal to 3. Okay. So we've done backpropagation partially through this computation graph. Let's go through the rest of this example on the next slide. So let's go to a cleaned up copy of the computation graph. And just to recap, what we've done so far is go backward here and figured out that dv is equal to 3. And again, the definition of dv, that's just the variable name of the code, is really dj dv. And we figured out that dA is equal to 3. And again, dA is the variable name in your code, and that's really the value of dj dA. And we'll sort of hand wave how, we've gone backwards on these two edges, like so. Now let's keep computing derivatives. Let's look at the value u. So what is dj du? Well, through a similar calculation as what we did before, we start off with u equals 6. If you bump up u to 6.001, then v, which is previous 11, goes up to 11.001, and so j goes from 33 to 33.003, and so the increase in j is 3x, so this is equal. And the analysis for u is very similar to the analysis we did for a. This is actually computed as dj dv times dv du, where this we had already figured out was 3, and this turns out to be equal to 1. So with kind of one more step of backpropagation, we end up computing that du is also equal to 3, and du is of course just this dj du. Now we just step through one last example in detail. So what is dj db, right? So imagine if you are allowed to change the value of b and you want to tweak b a little bit in order to minimize or maximize the value of j, right? So what is the derivative, or what's the slope of this function j when you change the value of b a little bit? It turns out that using the chain rule for calculus, this can be written as the product of two things. It's dj du times du db. And the reasoning is if you change b a little bit, so b goes from 3 to say 3.001, the way it'll affect j is it will first affect u. So how much does it affect u? Well, u is defined as b times c, right? So this will go from 6 when b is equal to 3 to now 6.002, right? Because c is equal to 2 in our example here. And so this tells us that du db is equal to 2, because when you bump up b by 0.001, u increases twice as much. So du db, this is equal to 2. And now we know that u has gone up twice as much as b has gone up. Well, what is dj du? We've already figured out that this is equal to 3. And so by multiplying these two out, we find that dj db is equal to 6. And again, here's the reasoning for the second part of the argument, which is we want to know when u goes up by 0.002, how does that affect j? The fact that dj du is equal to 3, that tells us that when u goes up by 0.002, j goes up 3 times as much. So j should go up by 0.006, right? So that comes from the fact that dj du is equal to 3. And if you check the math in detail, you will find that if b becomes 3.001, then u becomes 6.002, v becomes 11.002, right? So that's a plus u, so that's 5 plus u, and then j, which is equal to 3 times v, that ends up being equal to 33.006, right? And so that's how you get that dj db is equal to 6. And to fill that in, this is, if we go backwards, so this is db is equal to 6. And db really is the Python covariable name for dj db. And I won't go through the last example in great detail, but it turns out that if you also compute out dj, this turns out to be dj du times du, and this turns out to be 9. This turns out to be 3 times 3. I won't go through that example in detail, but so through this last step, it is possible to derive that dc is equal to. So the key takeaway from this video, from this example, is that when computing derivatives and computing all of these derivatives, the most efficient way to do so is through a right to left computation following the direction of the red arrows. And in particular, we'll first compute the derivative with respect to v, and then that becomes useful for computing the derivative with respect to a and the derivative with respect to u, and then the derivative with respect to u, for example, this term over here and this term over here, those in turn become useful for computing the derivative with respect to b and the derivative with respect to c. So that was the computation graph and how there's a forward or left to right calculation to compute the cost function such as j that you might want to optimize, and a backwards or a right to left calculation to compute derivatives. If you're not familiar with calculus or the chain rule, I know some of those details may have gone by really quickly, but if you didn't follow all the details, don't worry about it. In the next video, we'll go over this again in the context of logistic regression and show you exactly what you need to do in order to implement the computations you need to compute the derivatives for the logistic regression model. Welcome back. In this video, we'll talk about how to compute derivatives for you to implement gradient descent for logistic regression. The key takeaways will be what you need to implement. That is the key equations you need in order to implement gradient descent for logistic regression. But in this video, I want to do this computation using the computation graph. I have to admit, using the computation graph is a little bit of an overkill for deriving gradient descent for logistic regression. But I want to start explaining things this way to get you familiar with these ideas so that hopefully it'll make a bit more sense when we talk about full-fledged neural networks. But so with that, let's dive into gradient descent for logistic regression. To recap, we had set up logistic regression as follows. Your predictions y hat is defined as follows, where z is that. And if we focus on just one example for now, then the loss with respect to that one example is defined as follows, where a is the output of logistic regression and y is the ground truth label. So let's write this out as a computation graph. And for this example, let's say we have only two features, x1 and x2. So in order to compute z, we'll need to input w1, w2, and b in addition to the feature values x1 and x2. So these things in our computation graph get used to compute z, which is w1, x1 plus w2, x2 plus b. Draw a rectangular box around that. And then we compute y hat, or a, equals sigma of z. That's the next step in a computation graph. And then finally, we compute L, ay, and I won't copy the formula again. So in logistic regression, what we want to do is to modify the parameters w and b in order to reduce this loss. We've described the 4 propagation steps of how you actually compute the loss on a single training example. Now let's talk about how you can go backwards to compute the derivatives. Here's a cleaned up version of the diagram. Because what we want to do is compute derivatives with respect to this loss, the first thing we want to do, maybe going backwards, is to compute the derivative of this loss with respect to, so script over there, with respect to this variable a. And so in the code, you just use dA, right, to denote this variable. And it turns out that if you are familiar with calculus, you could show that this ends up being negative y over a plus 1 minus y over 1 minus a. And the way you do that is you take the formula for the loss, and if you're familiar with calculus, you can compute the derivative with respect to the variable lowercase a, and you get this formula. But if you're not familiar with calculus, don't worry about it. We'll provide the derivative formulas you need throughout this course. So if you're an expert in calculus, I'd encourage you to look up the formula for the loss from the previous slide and try taking the derivative with respect to a using calculus. But if you don't know enough calculus to do that, don't worry about it. Now, having computed this quantity, or dA, the derivative of your final output variable with respect to a, you can then go backwards. And it turns out that you can show dz, which this is the Python code variable name. This is going to be the derivative of the loss with respect to z. Or for L, you could really write the loss including a and y explicitly as parameters or not, right? Either type of notation is equally acceptable. We could show that this is equal to a minus y. Just a couple comments only for those of you that are expert in calculus. If you're not expert in calculus, don't worry about it. But it turns out that this, right, dl dz, this can be expressed as dl dA times dA dz. And it turns out that dA dz, this turns out to be a times 1 minus a. And dl dA, we had previously worked out over here. And so if you take these two quantities, dl dA, which is this term, together with dA dz, which is this term, and just take these two things and multiply them, you could show that the equation simplifies to a minus y. So that's how you derive it. And then this is really the chain rule that I briefly alluded to before. Okay, so feel free to go through that calculation yourself if you are knowledgeable about calculus, but if you aren't, all you need to know is that you can compute dz as a minus y, and I've already done the calculus for you. And then the final step in backpropagation is to go back to compute how much you need to change w and b. So in particular, you can show that the derivative with respect to w1, and in code we'll call this dw1, that this is equal to x1 times dz, and then similarly dw2, which is how much you want to change w2, is x2 times dz, and db is equal to dz. So if you want to do gradient descent with respect to just this one example, what you would do is the following. You would use this formula to compute dz, and then use these formulas to compute dw1, dw2, and db, and then you perform these updates. W1 gets updated as W1 minus learning rate alpha times dW1. W2 gets updated similarly, and B gets set as B minus the learning rate times dB. And so this would be one step of grade with respect to a single example. So you've seen how to compute derivatives and implement gradient descent for logistic regression with respect to a single training example. But to train your logistic regression model, you have not just one training example, you have an entire training set of M training examples. So in the next video, let's see how you can take these ideas and apply them to learning not just from one example, but from an entire training set. In a previous video, you saw how to compute derivatives and implement gradient descent with respect to just one training example for logistic regression. Now we want to do it for M training examples. To get started, let's remind ourselves of the definition of the cost function J. Cost function WB, which you care about, is this average, right? 1 over m, sum from I equals 1 through m of the loss when your algorithm output AI on the example Y, where AI is the prediction on the I've training example, which is sigma of Zi, which is equal to sigma of W transpose Xi plus B. Okay, so what we show in the previous slide is for any single training example, how to compute the derivatives when you have just one training example, right? So dw1, dw2, and db, with now the superscript I to denote the corresponding values you get if you were doing what we did on the previous slide, but just using the one training example, xi, yi. Oh, excuse me, missing an I there as well. So now you notice the overall cost function is the sum, or it's really the average, because of the 1 over m term, of the individual losses. So it turns out that the derivative with respect to, say, w1 of the overall cost function is also going to be the average of derivatives with respect to w1 of the individual loss terms. But previously we had already shown how to compute this term as, say, dw1i, right, which we on the previous slide show how to compute this on a single training example. So what you need to do is really compute these derivatives as we showed on the previous training example and average them, and this will give you the overall gradient that you can use to implement gradient descent. So I know that was a lot of details, but let's take all of this up and wrap this up into a concrete algorithm, so into what you should implement to get logistic regression with gradient descent working. So here's what you can do. Let's initialize j equals 0, dw1 equals 0, dw2 equals 0, db equals 0. And what we're going to do is use a for loop over the training set and compute the derivatives with respect to each training example and then add them up. All right, so here's what we do. For I equals 1 through m, so m is the number of training examples, we compute zi equals w transpose xi plus b. The prediction ai is equal to sigma of zi, and then let's add up j. J plus equals yi log ai plus 1 minus yi log 1 minus ai, and then let's put a negative sign in front of the whole thing. And then as we saw earlier, we have dzi, right, is equal to ai minus yi, and dw gets plus equals x1i dzi dw2 plus equals xi2 dzi. Oh, and I'm doing this calculation assuming that you have just two features, so that n is equal to 2. Otherwise, you do this for dw1, dw2, dw3, and so on. And then db plus equals dzi. And I guess that's the end of the for loop. And then finally, having done this for all m training examples, you would still need to divide by m because we're computing averages. So dw1 divide equals m. dw2 divide equals m, db divide equals m in order to compute averages. And so with all of these calculations, you've just computed the derivatives of the cost function j with respect to each of your parameters w1, w2, and b. Just a couple of details of what we're doing. We're using dw1 and dw2 and db as accumulators, right? So that after this computation, dw1 is equal to the derivative of your overall cost function with respect to w1, and similarly for dw2 and db. So notice that dw1 and dw2 do not have a superscript I because we're using them in this code as accumulators to sum over the entire training set. Whereas in contrast, dzi here, this was dz with respect to just one single training example. So that's why that had a superscript I to refer to the one training example I that's computed on. And so having finished all these calculations, to implement one step of gradient descent, you would implement w1 gets updated as w1 minus a learning rate times dw1, w2 gets updated as w2 minus learning rate times dw2, and b gets updated as b minus learning rate times db, where dw1, dw2, and db were, as computed. And finally, j here would also be a correct value for your cost function. So everything on this slide implements just one single step of gradient descent, and so you'd have to repeat everything on this slide multiple times in order to take multiple steps of gradient descent. In case these details seem too complicated, again, don't worry too much about it for now. Hopefully all this will be clearer when you go and implement this in the programming assignment. But it turns out there are two weaknesses with the calculation as we've implemented it here, which is that to implement logistic regression this way, you need to write two for loops. The first for loop is this for loop over the m training examples, and the second for loop is a for loop over all the features over here. Right, so in this example, we just had two features, so n is equal to 2, or nx equals 2. But if you have more features, you end up writing dw1, dw2, and you have similar computations for dw3, and so on down to dwn. So it seems like you need to have a for loop over the features, over all n features. When you're implementing deep learning algorithms, you find that having explicit for loops in your code makes your algorithm run less efficiently. And so in the deep learning era, we've moved to bigger and bigger data sets. And so being able to implement your algorithms without using explicit for loops is really important and will help you to scale to much bigger data sets. So it turns out that there are a set of techniques called vectorization techniques that allow you to get rid of these explicit for loops in your code. I think in the pre-deep learning era, that is before the rise of deep learning, vectorization was a nice to have. So you could sometimes do it to speed up your code and sometimes not. But in the deep learning era, vectorization, that is getting rid of for loops like this and like this, has become really important because we're more and more training on very large data sets, and so you really need your code to be very efficient. So in the next few videos, we'll talk about vectorization and how to implement all this without using even a single for loop. So with this, I hope you have a sense of how to implement logistic regression or gradient descent for logistic regression. Things will be clearer when you implement the programming exercise. But before actually doing the programming exercise, let's first talk about vectorization so that you can implement this whole thing, implement a single iteration of gradient descent without using any for loops. Welcome back. Vectorization is basically the art of getting rid of explicit for loops in your code. In the deep learning era, certainly in deep learning in practice, you often find yourself training on relatively large datasets because that's when deep learning algorithms tend to shine. And so it's important that your code run quickly because otherwise, if you're training on a big dataset, your code might take a long time to run and you just find yourself waiting a very long time to get a result. So in the deep learning era, I think the ability to perform vectorization has become a key skill. Let's start with an example. So what is vectorization? In logistic regression, you needed to compute z equals w transpose x plus b, where w was this column vector and x is also this vector. And maybe they're very large vectors if you have a lot of features. So w and x were both these Rn or Rnx dimensional vectors. So to compute W transpose X, if you had a non-vectorized implementation, you would do something like z equals 0, and then for I in range of nx, so for I equals 1 to nx, z plus equals wi, times xi. And then maybe you do z plus equals b at the end. So that's a non-vectorized implementation. And you find that that's going to be really slow. In contrast, a vectorized implementation would just compute w transpose x directly. In Python or in NumPy, the command you use for that is z equals np dot w comma x. So this computes w transpose x, and you can also just add b to that directly. And you find that this is much faster. Let's actually illustrate this with a little demo. All right, so here's my Jupyter notebook in which I'm going to write some Python code. So first let me import the NumPy library. So import this np, and so for example, I can create a as an array as follows: 2, 3, 4, and let's say print a. Now, having written this chunk of code, if I hit Shift Enter, then it executes the code. So it created the array a and it prints it out. Now, let's do the vectorization demo. I'm going to import the time library, since I'm going to use that in order to time how long different operations take. I'm going to create an array a, equals random dot rand. Let's create a million dimensional array, right, with random the values b equals np dot random dot rand, another million dimensional array. And now tick equals time dot time, so let's measure the current time. C equals np dot ab. Let's see, talk equals time dot time, and let's print. This is the vectorized version, right? So vectorized version, and so let's print out. Let's see, the last time. So let's talk minus tick times 1000, so that we can express this in milliseconds. So ms is milliseconds. Okay, so I'm going to hit Shift Enter. Okay, so that code took about 3 milliseconds, or this time 1.5. Okay, maybe about 1.5 or 3.5 milliseconds that time. So, it varies a little bit as I run it, but it looks like maybe on average it's taking like 1.5 milliseconds, maybe 2 milliseconds as I run this. All right, let's keep adding to this block of code. So let's now implement a non-vectorized version. Let's say c equals 0, then tick equals time dot time. And now let's implement a for loop for I in range of 1 million, right? Hope I got the number of zeros right. C plus equals AI times BI, and then talk equals time.time. Oops. And finally print, with an explicit for loop, the time it takes is this 1000 times talk minus tick plus ms, just to denote that we're doing this in milliseconds. Okay. Oh, and actually, let's do one more thing. Let's just print out the value of C we computed to make sure that it's the same value in both cases. Okay, so I'm going to hit Shift Enter to run this and check that out. So in both cases, the vectorized version and the non-vectorized version computed the same value. This is 250.286.989, so on. The vectorized version took 1.5 milliseconds. The explicit for loop, the non-vectorized version, took about 400, almost 500 milliseconds. So the non-vectorized version took, something like 300 times longer than the vectorized version, right? And so with this example, you see that if only you remember to vectorize your code actually runs, over 300 times faster. Well, let's just run it again, right? Here's run it again. Yeah, vectorized version 1.5 milliseconds, and the for loop took 481 milliseconds. So again, about 300 times slower to do the explicit for loop. So 300x slowdown is the difference between your code taking maybe 1 minute to run versus it taking, say, 5 hours to run. And when you are implementing deep learning algorithms, you can really get the result back faster and iterate much faster if you vectorize your code. So some of you might have heard that a lot of scalable deep learning implementations are done on a GPU, on a graphics processor unit. But all the demos I did just now in the Jupyter Notebook were actually on a CPU. And it turns out that both GPU and CPUs have parallelization instructions. They're sometimes called SIMD instructions. This stands for single instruction, multiple data. But what this basically means is that if you use built-in functions such as this np function or other functions that don't require you explicitly implementing a for loop, it enables Python and NumPy to take much better advantage of parallelism to do your computations much faster. And this is true both for computations on CPUs and computations on GPUs. It's just that GPUs are remarkably good at these SIMD calculations, but CPUs are actually also not too bad at them, maybe just not as good as GPUs. So you've seen how vectorization can significantly speed up your code. The rule of thumb to remember is, whenever possible, avoid using explicit for loops. Let's go on to the next video to see some more examples of vectorization and also start to vectorize logistic regression. In the previous video, you saw a few examples of how vectorization, by using built-in functions and by avoiding explicit for loops, allows you to speed up your code significantly. Let's take a look at a few more examples. The rule of thumb to keep in mind is, when you're programming your neural networks or when you're programming logistic regression, whenever possible, avoid explicit for loops. And it's not always possible to never use a for loop, but when you can use a built-in function or find some other way to compute whatever you need, it will often go faster than if you had an explicit for loop. Let's look at another example. If ever you want to compute a vector u as the product of a matrix A and another vector v, then the definition of a matrix multiply is that your ui is equal to sum over j, aij, bj, right? That's how you define ui. And so the non-vectorized implementation of this would be, to set u equals np dot zeros, maybe n by 1, and then, for I and so on, for j and so on, right? And then ui plus equals, aij times bj. So now this has two for loops looping over both I and j. So that's the non-vectorized version. The vectorized implementation would be to say u equals np dot A comma V. And the implementation on the right, the vectorized version, now eliminates two different for loops, and it's going to be way faster. Let's go through one more example. Let's say you already have a vector V in memory, and you want to apply the exponential operation on every element of, say, this vector V. So you compute U equals, vector that's e to the V1, e to the V2, and so on down to e to the Vn. So this would be a non-vectorized implementation, right? Which is that first you initialize U to a vector of zeros, and then you have a for loop that computes the elements one at a time. But it turns out that Python and NumPy have many built-in functions that allow you to compute these vectors with just a single call to a single function. So what I would do to implement this is import NumPy as np, and then what you can just call U equals np dot e to the v. And so notice that whereas previously you had an explicit for loop with just one line of code here, this v is an input vector, u is an output vector, you've gotten rid of the explicit for loop, and the implementation on the right will be much faster than the one needing an explicit for loop. In fact, the NumPy library has many other vector value functions. So np.log of v will compute the element-wise log, np.abs computes the absolute value, np.maximum computes the element-wise maximum, so you can take the max of every element of v with 0, v star star 2, this takes the element-wise square of each element of v, 1 over v takes the element-wise inverse, and so on. So whenever you're tempted to write a for loop, take a look and see if there's a way to call a NumPy built-in function to do it without that for loop. So let's take all of these learnings and apply it to our logistic regression gradient descent implementation and see if we can at least get rid of one of the two for loops we had. So here's our code for computing the derivatives for logistic regression. And we had two for loops. One was this one up here, and the second one was this one, right? So in our example, we had n or nx equals 2, but if you had more features than just two features, then you need to have a for loop over dw1, dw2, dw3, and so on. So it's as if there's actually a for j equals 1 to nx, dwj gets updated, right? So we like to eliminate this second for loop. That's what we'll do on the slide. So the way we'll do so is that instead of explicitly initializing dw1, dw2, and so on to zeros, we're going to get rid of this and instead make dw a vector. So we're going to set dw equals np.zeros, and let's make this a nx by 1 dimensional vector. Then here, instead of this for loop over the individual components, we just use this vector value operation, dw plus equals xi times dzi. And then finally, instead of this, we will just have dw device equals m. So now we've gone from having two for loops to just one for loop. We still have this one for loop that loops over the individual training examples. So I hope this video gave you a sense of vectorization, and by getting rid of one for loop, your code will already run faster. But it turns out we could do even better. So in the next video, we'll talk about how to vectorize logistic regression even further, and you see a pretty surprising result that without using any for loops, without needing a for loop over the training examples, you could write code to process the entire training set. So pretty much all at the same time. So let's see that in the next video. We've talked about how vectorization lets you speed up your code significantly. In this video, we'll talk about how you can vectorize your implementation of logistic regression so that you can process an entire training set, that is, implement a single iteration of gradient descent with respect to an entire training set without using even a single explicit for loop. I'm super excited about this technique, and when we talk about neural networks later, without using even a single explicit for loop. Let's get started. Let's first examine the forward propagation step of logistic regression. So if you have m training examples, then to make a prediction on the first example, you need to compute that, right? Compute z using this familiar formula, then compute the activation, let's compute y hat on the first example. Then to make a prediction on the second training example, you need to compute that. Then to make a prediction on the third example, you need to compute that, and so on. And you might need to do this m times if you have m training examples. So it turns out that in order to carry out the forward propagation step, that is to compute these predictions on all m training examples, there is a way to do so without needing an explicit for loop. Let's see how you can do it. First, remember that we defined the matrix capital X to be your training inputs, stacked together in different columns like this, right? So this is a matrix that is a nx by m matrix. So I'm writing this as a Python NumPy shape, but this just means that x is a nx by m dimensional matrix. Now, the first thing I want to do is show how you can compute z1, z2, z3, and so on, all in one step. In fact, with one line of code. So I'm going to construct a 1 by m matrix. This is really a row vector, where I'm going to compute z1, z2, and so on, down to zm, all at the same time. It turns out that this can be expressed as W transpose, the capital matrix X, plus, and then this vector, B, B, and so on, B, where this thing, this B, 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 B thing is a 1 by m vector, or 1 by m matrix, or that is a m-dimensional row vector. So depending on how familiar you are with matrix multiplication, you might see that W transpose x1, x2, and so on through xm, that W transpose is going to be a row vector, right? So this W transpose will be a row vector like that. And so this first term will evaluate to W transpose x1, W transpose x2, and so on, dot, 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 W transpose xm. And then when you add this second term, B, 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 and so on, you end up adding B to each element. So you end up with another 1 by n vector, where that's the first element, that's the second element, and so on, and that's the nth element. And if you refer to the definitions above, this first element is exactly the definition of z1. The second element is exactly the definition of z2, and so on. So just as x was what you obtained when you took your training examples and stacked them next to each other, stacked them horizontally, I'm going to define capital Z to be this, where you take the lowercase z's and stack them horizontally. Okay, so when you stack the lowercase x's corresponding to different training examples horizontally, you get this variable capital X. In the same way, when you take these lowercase z variables and stack them horizontally, you get this variable, which I'm going to denote via capital Z. And it turns out that in order to implement this, the NumPy command is capital Z equals np dot w dot t, that's W transpose X, and then plus B. Now, there is a subtlety in Python, which is that here, B is a row number, or if you want, is a, 1 by 1 matrix, so it's just a normal row number. But when you add this vector to this real number, Python automatically takes this real number b and expands it out to this 1 by m row vector. So in case this operation seems a little bit mysterious, this is called broadcasting in Python, and you don't have to worry about it for now. We'll talk about it some more in the next video. But the takeaway is that with just one line of code, with this line of code, you can calculate capital Z, and capital Z is going to be a 1 by m matrix that contains all of the lowercase z's, lowercase z1 through lowercase zm. So that was Z. How about these values, A, right? What we'd like to do next is find a way to compute A1, A2, and so on through AM all at the same time. And just as stacking lowercase x's resulted in capital X, and stacking means stacking horizontally, lowercase z's results in capital Z, stacking lowercase a's is going to result in a new variable which we're going to define as capital A. And in the program assignment, you see how to implement a vector-valued sigmoid function so that the sigmoid function inputs this capital Z as a variable and very efficiently outputs capital A. So you see the details of that in the programming assignment. So just to recap, what we've seen on this slide is that instead of needing to loop over m training examples to compute lowercase z and lowercase a one at a time, you can implement this one line of code to compute all the z's at the same time, and then this one line of code with appropriate implementation of lowercase sigma to compute all the lowercase a's all at the same time. So this is how you implement a vectorized implementation of the forward propagation for all m training examples at the same time. So to summarize, you've just seen how you can use vectorization to very efficiently compute all the activations, all the lowercase a's, sort of at the same time. Next, it turns out you can also use vectorization to very efficiently compute the backward propagation, to compute the gradients. Let's see how you can do that in the next video. In the previous video, you saw how you can use vectorization to compute the predictions, the lowercase a's, for an entire training set all sort of at the same time. In this video, you see how you can use vectorization to also perform the gradient computations for all m training examples, again all sort of at the same time. And then at the end of this video, we'll pull it all together and show how you can derive a very efficient implementation of logistic regression. So you will remember that for the gradient computation, what we did was we computed dz1 for the first example, which is going to be a1 minus y1, and then dz2 equals a2 minus y2, and so on. So, and so on for all m training examples. So what we're going to do is define a new variable, d capital Z, which is going to be dz1, dz2, right, dzm. Again, all the d lowercase z variables stacked horizontally, so this would be a 1 by m matrix, or alternatively a m-dimensional row vector. Now recall that from the previous slide, we'd already figured out how to compute capital A, which was this A1 through AM. And we had defined capital Y as Y1 through YM, also, stacked horizontally. So based on these definitions, maybe you can see for yourself that dz can be computed as just A minus Y, because this is going to be equal to a1 minus y1 is going to be the first element, a2 minus y2 is going to be the second element, and so on. And so this first element, a1 minus y1, is exactly the definition of dz1. The second element is exactly the definition of dz2, and so on. So with just one line of code, you can compute all of this at the same time. Now, in the previous implementation, we've gotten rid of one for loop already, but we still had this second for loop over training examples. So we initialized dw to 0, to a vector of zeros, but then we still had to loop over training examples where we have dw plus equals x1 times dz1 for the first training example, dw plus equals x2, dz2, and so on. So we do the m times, and then dw divide equals by m. And similarly for b, right? db was initialized as 0, and then db plus equals dz1, db plus equals dz2, down to, dzm, and then db divide equals m. So that's what we had in the previous implementation. We'd already gotten rid of one for loop, so at least now dw is a vector, and we weren't separately updating dw1, dw2, and so on. So we've gotten rid of that already, but we still had a for loop over the m examples in the training set. So let's take these operations and vectorize them. Here's what we can do. For the vectorized implementation of db, what it's doing is basically summing up all of these dz's and then dividing by m. So db is basically 1 over m, sum from I equals 1 through m of dzi, and well, all the dz's are in that row vector. And so in Python, what you do is implement 1 over m times np dot sum of dz, right? So just take this variable and call the np dot sum function on it, and that will give you db. How about dw? I'll just write out the correct equations. You can verify it's the right thing to do. dw turns out to be 1 over m times the matrix x times dz transpose. And to kind of see why that's the case, this is equal to 1 over m, then the matrix x is x1 through xm, right, stacked up in columns like that, and dz transpose is going to be dz1 down to dzm, like so. And so if you figure out what this matrix times this vector works out to be, this turns out to be 1 over m times x1 dz1 plus dot 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 plus xm dzm, right? And so this is a n by 1 vector, and this is what you actually end up with dw, because dw was taking these xi, dzi, and adding them up, and so that's what exactly this matrix vector multiplication is doing. And so again, with one line of code, you can compute dw. So the vectorized implementation of the derivative calculations is just this. You use this line to implement db, and use this line to implement dw. And notice that without a for loop over the training set, you can now compute the updates you want to your parameters. So now let's put it all together into how you would actually implement logistic regression. So this is our original highly inefficient non-vectorized implementation, where so the first thing we've done in the previous video was get rid of this for loop, right? So instead of looping over dw1, dw2, and so on, we had replaced this with a vector value dw, and we'll just say this is dw plus equals xi, which is now a vector, times dzi. But now we'll see that we could also get rid of not just the for loop below, but also get rid of this for loop. So here's how you do it. So using what we had from the previous slides, you would say capital Z is equal to W transpose X plus B, and the code you write is capital Z equals NP dot W transpose X plus B, and then A equals sigmoid of capital Z. So you've now computed all of this and all of this for all the values of I. Next, on the previous slide, we said you would compute dz equals capital A minus capital Y. So now you computed all of this for all the values of I. Then finally, dw equals 1 over m x dz transpose, and dB equals 1 over m of, np dot sum dz. So you've just done forward propagation and back propagation, really computing the predictions and computing the derivatives on all m training examples without using a for loop. And so the gradient descent update then would be, w gets updated as w minus the learning rate times dw, which we just computed above, and b gets updated as b minus the learning rate times db. Because sometimes it's putting colons there to denote this as assignment. But I guess I haven't been totally consistent with that notation. But with this, you've just implemented a single iteration of gradient descent for logistic regression. Now, I know I said that we should get rid of explicit for loops whenever you can, but if you want to implement multiple iterations of gradient descent, then you still need a for loop over the number of iterations. So if you want to have 1,000 iterations of gradient descent, you might still need a for loop over the iteration number. There's an outermost for loop like that, and I don't think there's any way to get rid of that for loop. But I do think it's incredibly cool that you can implement at least one iteration of gradient descent without needing to use a for loop. So that's it. You now have a highly vectorized and highly efficient implementation of gradient descent for logistic regression. There's just one more detail that I want to talk about in the next video, which is in our description here, I briefly alluded to this technique called broadcasting. Broadcasting turns out to be a technique that Python and NumPy allows you to use to make certain parts of your code also much more efficient. So let's see some more details of broadcasting in the next video. In the previous video, I mentioned that broadcasting is another technique that you can use to make your Python code run faster. In this video, let's delve into how broadcasting in Python actually works. Let's motivate broadcasting with an example. In this matrix, I've shown the number of calories from carbohydrates, proteins, and fats in 100 grams of 4 different foods. So for example, 100 grams of apples turns out has 56 calories from carbs and much less from proteins and fats. Whereas in contrast, 100 grams of beef has 104 calories from protein, 135 calories from fat. Now, let's say your goal is to calculate the percentage of calories from carbs, proteins, and fats for each of the 4 foods. So for example, if you look at this column and add up the numbers in that column, you get that 100 grams of apple has 56 plus 1.2 plus 1.8. So that's 59 calories. And so as a percentage, the percentage of calories from carbohydrates in an apple would be 56 over 59. That's about 94.9%. So most of the calories in an apple come from carbs, whereas in contrast, most of the calories of beef come from protein and fat, and so on. So the calculation you want is really to sum up each of the 4 columns of this matrix to get the total number of calories in 100 grams of apple, beef, eggs, or potatoes, and then to divide throughout the matrix so as to get the percentage of calories from carbs, proteins, and fats for each of the 4 foods. So the question is, can you do this without an explicit for loop? Let's take a look at how you could do that. What I'm going to do is show you how you can set, say, this matrix equal to a 3x4 matrix A, and then with one line of Python code, we're going to sum down the columns. So we're going to get 4 numbers corresponding to the total number of calories in these 4 different types of food, 100 grams of these 4 different types of food. And I'm going to use a second line of Python code to divide each of the 4 columns by their corresponding sum. If that verbal description wasn't very clear, hopefully it'll be clearer in a second when we look at the Python code. So here we are in the Jupyter notebook. I've already written this first piece of code to pre-populate the matrix A with the numbers we had just now. So let me hit Shift Enter and just run that. So there's the matrix A. And now here are the two lines of Python code. First, I'm going to compute cal equals A dot sum, and axis equals 0 means the sum vertically. Say more about that in a little bit. And then let's print cal. So with sum vertically, so as we say just now, 59 is the total number of calories in the apple. 239 was the total number of calories in the beef and eggs and potato and so on. And then we're going to compute percentage equals A over cal dot reshape 1 by 4. Actually, we want percentages, so multiply by 100 here. And then let's print percentage. Let's run that. And so with that command, we've taken the matrix A and divided it by this 1 by 4 matrix, and this gives us the matrix of percentages. So as we worked out kind of by hand just now, in the apple, that was the first column, 94.9% of the calories are from carbs. Let's go back to the slides. So just to repeat the two lines of code we had, this is what we had written out in the Jupyter notebook. To add a bit of detail, this parameter axis equals 0 means that you want Python to sum vertically. So this is axis 0, means to sum vertically, whereas the horizontal axis is axis 1. So if we were to write axis 1, it'll sum horizontally instead of sum vertically. And then this command here, this is an example of Python broadcasting where you take a matrix A. So this is a 3 by 4 matrix, and you divide it by a 1 by 4 matrix. And technically, after this first line of code, cal, the variable cal, is already a 1 by 4 matrix. So technically, you don't need to call reshape here again. So that's actually a little bit redundant. But when I'm writing Python codes, if I'm not entirely sure what matrix, what are the dimensions of my matrix, I often would just call a reshape command just to make sure that is the right column vector or the row vector or whatever you want it to be. The reshape command is a constant time. It's an order 1 operation, so it's very cheap to call. So don't be shy about using the reshape command to make sure that your matrices are the size you need it to be. Now, let's explain in greater detail how this type of operation works, right? We had a 3 by 4 matrix and we divided it by a 1 by 4 matrix. So how can you divide a 3 by 4 matrix by a 1 by 4 matrix or by 1 by 4 vector? Let's go through a few more examples of broadcasting. If you take a 4 by 1 vector and add it to a number, what Python will do is take this number and auto-expand it into a 4 by 1 vector as well, as follows. And so the vector 1, 2, 3, 4 plus the number 100 ends up with that vector on the right. You're adding 100 to every element. And in fact, we used this form of broadcasting where that constant was the parameter b in an earlier video. And this type of broadcasting works with both column vectors and row vectors. And in fact, we used a similar form of broadcasting earlier with the constant we're adding to a vector being the parameter b in logistic regression. Here's another example. Let's say you have a 2 by 3 matrix and you add it to this 1 by n matrix. So the general case would be if you have some m by n matrix here, and you add it to a 1 by n matrix. What Python will do is copy the matrix m times to turn this into an m by n matrix. So instead of this 1 by 3 matrix, it'll copy it twice in this example to turn it into this also 2 by 3 matrix. And they'll add these, so you end up with this sum on the right. Okay, so you added 100 to the first column, added 200 to the second column, added 300 to the third column. And this is basically what we did on the previous slide, except that we use a division operation instead of an addition operation. Just one last example. What if you have a m by n matrix and you add this to an m by 1 vector, an n by 1 matrix. Then this will copy this n times horizontally, so you end up with an n by n matrix. So as you can imagine, it will copy it horizontally 3 times and add those. So when you add them, you end up with this. So we've added 100 to the first row and added 200 to the second row. Here's the more general principle of broadcasting in Python. If you have an m by n matrix, and you add or subtract or multiply or divide with a 1 by n matrix, then this will copy it m times into an m by n matrix, and then apply the addition, subtraction, multiplication, or division element-wise. If conversely, you were to take the m by n matrix and add, subtract, multiply, or divide by an m by 1 matrix, then also this will copy it now n times and turn that into an m by n matrix, and then apply the operation element-wise. Just one other form of broadcasting, which is if you have an m by 1 matrix, so that's really a column vector, like 1, 2, 3, and you add, subtract, multiply, or divide by a row number, so maybe a 1 by 1 matrix, so such as that, plus 100, then you end up copying this row number m times until you also get another m by 1 matrix, and then you perform the operation, such as addition in this example, element-wise. And something similar also works for row vectors. The fully general version of broadcasting can do even a little bit more than this. If you're interested, you can read the documentation for NumPy and look up broadcasting in that documentation. That gives an even slightly more general definition of broadcasting, but the ones on this slide are the main forms of broadcasting that you end up needing to use when you implement a neural network. Before we wrap up, just one last comment, which is for those of you that are used to programming in either MATLAB or Octave, if you've ever used the MATLAB or Octave function bsxfun, in neural network programming, bsxfun does something similar, not quite the same, but is often used for a similar purpose as what we use broadcasting in Python for. But this is really only for very advanced MATLAB and Octave users. If you've not heard of this, don't worry about it. You don't need to know it when you're coding up neural networks in Python. So that was broadcasting in Python. I hope that when you do the programming homeworks, that broadcasting will allow you to not only make your code run faster, but also help you get what you want done with fewer lines of code. Before you dive into the programming exercise, I want to share with you just one more set of ideas, which is that there's some tips and tricks that I found reduces the number of bugs in my Python code, and that I hope will help you too. So with that, let's talk about that in the next video. The ability of Python to allow you to use broadcasting operations, and more generally, the great flexibility of the Python NumPy programming language is, I think, both a strength as well as a weakness of the programming language. I think it's a strength because the great expressivity of the language, the great flexibility of the language lets you get a lot done, with even just a single line of code. But it's also a weakness because with broadcasting and this great amount of flexibility, sometimes it's possible you can introduce very subtle bugs or very strange looking bugs if you aren't familiar with all of the intricacies of how broadcasting and how features like broadcasting work. For example, if you take a column vector and add it to a row vector, you might expect it to throw up a dimension mismatch or a type error or something. But you might actually get back a matrix as a sum of a row vector and a column vector. So there is an internal logic to these strange effects of Python, but if you aren't familiar with Python, now I've seen some students have very strange, very hard to find bugs. So what I want to do in this video is share with you a couple of tips and tricks that have been very useful for me to eliminate or simplify and eliminate a lot of the strange looking bugs in my own code. And I hope that with these tips and tricks, you also be able to much more easily write bug-free Python and NumPy code. To illustrate one of the less intuitive effects of Python NumPy, especially how you construct vectors in Python NumPy, let me do a quick demo. Let's say I set A equals np.random.randn5. So this creates a 5 random Gaussian variables stored in an array A. And so let's print A. And now it turns out that the shape of A, when you do this, is this 5 comma structure. And so this is called a rank 1 array in Python, and it's neither a row vector nor a column vector. And this leads it to have some slightly non-intuitive effects. So for example, if I print A transpose, it ends up looking the same as A. So A and A transpose end up looking the same. And if I print the inner product between A and A transpose, you might think A times A transpose is maybe the outer product, should give you a matrix maybe. But if I do that, you instead get back a number. So what I would recommend is that when you're coding neural networks, that you just not use data structures where the shape is this 5 comma or n comma rank 1 array. Instead, if you set A to be this 5 by 1, then this commits A to be a 5 by 1 column vector. And whereas previously A and A transpose look the same, if you now print A transpose, now A transpose is a row vector. Notice one subtle difference. In this data structure, there are 2 square brackets when you print A transpose, whereas previously there was 1 square bracket. So that's the difference between this is really a 1 by 5 matrix versus one of these are rank 1 arrays. And if you print, say, the product between A and A transpose, then this gives you the outer product of a vector, right? And so the outer product of a vector gives you a matrix. So let's look in greater detail at what we just saw here. The first command that we ran just now was this, and this created a data structure where A.shape was this funny thing 5 comma, and so this is called a rank 1 array. And this is a very funny data structure. It doesn't behave consistently as either a row vector nor a column vector, which makes some of its effects non-intuitive. So what I'm going to recommend is that when you're doing your programming exercises, or in fact when you're implementing logistic regression or neural networks, that you just do not use these rank 1 arrays. Instead, if every time you create an array, you commit to making it either a column vector, so this creates a 5 by 1 vector, or commit to making it a row vector, then the behavior of your vectors will maybe be easier to understand. So in this case, A.shape is going to be equal to 5 comma 1, and so this behaves a lot like or in fact this is a column vector. And that's why you can think of this as a 5 by 1 matrix or as a column vector. And here, A.shape is going to be 1 comma 5, and this behaves consistently as a row vector. So when you need a vector, I would say either use this or this, but not a rank 1 array. One more thing that I do a lot in my code is if I'm not entirely sure what's the dimension of one of my vectors, I'll often throw in an assertion statement like this to make sure in this case that this is a 5 by 1 vector, so this is a column vector. These assertions are really inexpensive to execute, and they also help to serve as documentation for your code. So don't hesitate to throw in assertion statements like this if you feel like it. And then finally, if for some reason you do end up with a rank 1 array, you can reshape this A equals A.reshape into say a 5 by 1 array or a 1 by 5 array, so that it behaves more consistently as either a column vector or a row vector. So I've sometimes seen students end up with very hard to track down bugs because of some of the non-intuitive effects of rank 1 arrays. By eliminating rank 1 arrays on my own code, I think my code became simpler, and I did not actually find it restrictive in terms of things I could express in code to just never use a rank 1 array. And so takeaways are, to simplify your code, don't use rank 1 arrays. Always use either n by 1 matrices, basically column vectors, or 1 by n matrices, or basically row vectors. Feel free to toss a lot of assertion statements to double check the dimensions of your matrix using arrays, and also, don't be shy about calling the reshape operation to make sure that your matrices or your vectors are the dimension that you need it to be. So I hope that this set of suggestions helps you to eliminate a class of bugs that from Python code and makes the programming exercise easier for you to complete. With everything you've learned, you're just about ready to tackle your first programming assignment. Before you do that, let me just give you a quick tour of IPython notebooks in Coursera. Here's the Jupyter IPython notebook that you can get to on Coursera. Let me just quickly show you a few features of this. The instructions are written right here in the text in the IPython notebook, and these little light gray blocks are blocks of code. So occasionally you see in these blocks something that looks like this. There's start code here and end code here. To do the programming exercise, please make sure to write your code between the start code here and end code here. So, for example, print hello world, right? And then to execute a code block, you can hit Shift Enter, and then to execute this code block, which I guess we just wrote print hello world, so that printed hello world. To run a cell, you can also, to run one of these code blocks of the cell, you can also click cell and then run cell, so that executes this. It's possible that on your computer, the keyboard shortcut for cell run cell might be different than Shift Enter, but on both my Mac as well as on my PC is Shift Enter, so it might be the same for you as well. Now, when you're reading the instructions, if you accidentally double click on it, you might end up with this markdown language. If you end up with this funny looking text, to convert it back to the nice looking text, just run this cell. So either go to cell, run cell, or I'm going to hit Shift Enter, and that basically executes the markdown and turns it back into this nice looking code. Just a couple more tips. When you execute code like this, it actually runs on a kernel, on a piece of code that runs on the server. If you're running an excessively large job, or if you leave a computer for a very long time, or something goes wrong, your internet connection or something, there is a small chance that the kernel on the back end might die, in which case just click kernel and then restart kernel, and hopefully that will reboot the kernel and make it work again. So that shouldn't happen if you're just running relatively small jobs and you just started up the IPython notebook. But if you see an error message that the kernel has died or something, you can try kernel restart. Finally, in an IPython notebook like this, there may be multiple blocks of code. So even if an earlier block of code doesn't have any graded code, be sure to execute this block of code, because in this example, it imports NumPy as NP and so on, and sets up some of the variables that you might need in order to execute the lower down blocks of code. So be sure to execute the ones on top, even if you aren't asked to write any code in them. And finally, when you're done implementing your solutions, there's this blue Submit Assignment button here on the upper right, and we click that, it will submit your solutions for grading. I've found that the interactive command shell nature of IPython notebooks to be very useful for letting you quickly implement a few lines of code, see an outcome, learn and iterate quickly. And so I hope that the programming exercises in the Coursera Jupyter IPython notebooks will help you quickly learn and experiment and see how to implement these learning algorithms. There's one more video after this. There's an optional video that talks about the cost function for logistic regression. You can watch that or not. Either way is perfectly fine. But either way, best of luck with the week 2 programming assignment. And I also look forward to seeing you at the start of the week 3 materials. In an earlier video, I've written down a form for the cost function for logistic regression. In this optional video, I want to give you a quick justification for why we like to use that cost function for logistic regression. To quickly recap, in logistic regression, we have that the prediction y hat is sigmoid of w transpose x plus b, where sigmoid is this familiar function. And we said that we want to interpret y hat as the probability that y is equal to 1 given x. So we want our algorithm to output y hat as the chance that y is equal to 1 for a given set of input features x. So another way to say this is that if y is equal to 1, then the chance of y given x is equal to y hat. And conversely, if y is equal to 0, then the chance that y was 0 was 1 minus y hat, right? So if y hat was the chance that y is equal to 1, then 1 minus y hat is the chance that y is equal to 0. So let me take these last two equations and just copy them to the next slide. So what I'm going to do is take these two equations, which basically define p of y given x, for the two cases of y equals 0 or y equals 1. And I'm going to take these two equations and summarize them into a single equation. And just to point out, y has to be either 0 or 1 because we're in binary classification, so y equals 0 or 1 are the only two possible cases, right? But so I'm going to take these two equations and summarize them as follows. Let me just write out what it looks like, then we'll explain why it looks like that. It's 1 minus y hat to the power of 1 minus y. So it turns out this one line summarizes the two equations on top. Let me explain why. So in the first case, suppose y is equal to 1, right? So if y is equal to 1, then this term ends up being y hat, because that's y hat to the power of 1. This term ends up being 1 minus y hat to the power of 1 minus 1, so that's the power of 0. But anything to the power of 0 is equal to 1, so that goes away. And so this equation just says p of y given x equals y hat when y is equal to 1. So, that's exactly what we wanted. Now, how about the second case? What if y equals 0? If y is equal to 0, then this equation above is p of y given x equals y hat to the 0, but anything to the power of 0 is equal to 1, so that's just equal to 1 times 1 minus y hat to the power of 1 minus y. So 1 minus y is 1 minus 0, so this is just 1. And so this is equal to 1 times 1 minus y hat, which is just equal to 1 minus y hat. And so here we have that if y equals 0, p of y given x is equal to 1 minus y hat, which is exactly what we wanted above. So what we've just shown is that this equation is a correct definition for p of y given x. Now, finally, because the log function is a strictly monotonically increasing function, maximizing log of p of y given x should give you a similar result as optimizing p of y given x. And if you compute log of p of y given x, that's equal to log of y hat to the power of y, 1 minus y hat to the power of 1 minus y. And so that simplifies to y log y hat plus 1 minus y times log 1 minus y hat, right? And so this is actually negative of the loss function that we had defined previously. And there's a negative sign there because usually if you're training a learning algorithm, you want to make probabilities large, whereas in logistic regression, we're expressing this, we want to minimize the loss function. So minimizing the loss corresponds to maximizing the log of the probability. So this is what the loss function on a single example looks like. How about the cost function, the overall cost function on the entire training set on m examples? Let's figure that out. So the probability of all the labels in the training set, right, I'm writing this out a little bit informally, is if you assume that the training examples are drawn independently or drawn IID, identically independently distributed, then the probability of the examples is the product of probabilities. So the product from I equals 1 through m of p of yi given xi. And so if you want to carry out maximum likelihood estimation, right, then you want to find the parameters that maximizes the chance of your observations in the training set. But maximizing this is the same as maximizing the log, so I'm just put logs on both sides. So log of the probability of the labels in the training set is equal to log of a product is the sum of a log, so that's sum from I equals 1 through m of log p of yi given xi. And we had previously figured out on the previous slide that this is negative L of y hat I, yi. And so in statistics, there's a principle called the principle of maximum likelihood estimation, which just means to choose the parameters that maximizes this thing, or in other words, that maximizes, this thing, right? Negative sum from I equals 1 through m, L of y hat I, yi. And I just moved the negative sign outside the summation. So this justifies the cost we had for logistic regression, which was J of WB of this. And because we now want to minimize the cost, instead of maximize the likelihood, we've gotten rid of the minus sign. And then finally, for convenience, or to make sure that our quantities are better scaled, we just add a 1 over m extra scaling factor there. But so to summarize, by minimizing this cost function J of WB, we're really carrying out maximum likelihood estimation with the logistic regression model under the assumption that our training examples were IID, or identically and independently distributed. So thank you for watching this video, even though this is optional. I hope this gives you a sense of why we use the cost function we do for logistic regression. And with that, I hope you go on to the exercises, the problem exercise and the quiz questions for this week. Best of luck with both the quizzes and the problem exercise. Welcome back. In this week, you learned to implement a neural network. Before diving into the technical details, I wanted in this video to give you a quick overview of what you'll be seeing in this week's videos. So if you don't follow all the details in this video, don't worry about it. We'll delve into technical details in the next few videos. But for now, let's give a quick overview of how you implement a neural network. Last week, we had talked about logistic regression, and we saw how this model corresponds to the following computation graph, where you'd input the features x and parameters w and b. That allows you to compute z, which is then used to compute a, and we were using a interchangeably with this output y hat, and then you can compute the loss function L. A neural network looks like this, and as I'd already previously alluded, you can form a neural network by stacking together a lot of little sigmoid units. Whereas previously, this node corresponds to two steps of calculations. The first is to compute the z value, second is to compute this a value. In this neural network, this stack of nodes will correspond to a z-like calculation like this, as well as an a-like calculation like that. And then that node will correspond to another z and another a-like calculation. So the notation, which we'll introduce later, will look like this. First, we'll input the features x together with some parameters w and b, and this will allow you to compute z1. So new notation that we'll introduce is that we'll use superscript square bracket 1 to refer to quantities associated with this stack of nodes. It's called a layer. And then later we'll use superscript square bracket 2 to refer to quantities associated with that node. Really, that's called another layer of the neural network. And the superscript square brackets, like we have here, are not to be confused with the superscript round brackets, which we use to refer to individual training examples. So whereas x superscript round bracket I refer to the ith training example, superscript square bracket 1 and 2 refer to these different layers, layer 1 and layer 2 in this neural network. But so going on, after computing z1, similar to logistic regression, there'll be a computation to compute a1, and that's just sigmoid of z1, and then you compute z2 using another sort of linear equation, and then compute a2, and a2 is the final output of the neural network and will also be used interchangeably with y hat. So I know that was a lot of details, but the key intuition to take away is that whereas for logistic regression, we had this z followed by a calculation, in this neural network here we just do it multiple times. There's a z followed by an a calculation and a z followed by an a calculation, and then you finally compute the loss at the end. And you remember that for logistic regression, we had this backward calculation in order to compute derivatives, right? So computing dA dz, and so on. So in the same way, in a neural network, we'll end up doing a backward calculation that looks like this, in which you end up computing dA2, dz2, that allows you to compute dw2, db2, and so on, in this sort of a right to left backward calculation that is denoting with the red arrows. So that gives you a quick overview of what a neural network looks like. It's basically taking logistic regression and repeating it twice. I know there was a lot of new notation, a lot of new details. Don't worry about it if you didn't follow everything. We'll go into the details more slowly in the next few videos. So let's go on to the next video. We'll start to talk about the neural network representation. See me draw a few pictures of neural networks. In this video, we'll talk about exactly what those pictures means. In other words, exactly what those little neural networks we've been drawing represent. And we'll start with focusing on the case of neural networks with what's called a single hidden layer. Here's a picture of a neural network. Let's give different parts of these pictures some names. We have the input features x1, x2, x3 stacked up vertically, and this is called the input layer of the neural network. So maybe not surprisingly, this contains the inputs to the neural network. Then there's another layer of circles, and this is called a hidden layer of the neural network. I'll come back in a second to say what the word hidden means. But the final layer here is formed by, in this case, just one node, and this single node layer is called the output layer and is responsible for generating the predicted value y hat. In a neural network that you train with supervised learning, the training set contains values of the inputs x as well as the target outputs y. So the term hidden layer refers to the fact that in the training set, the true values for these nodes in the middle are not observed. That is, you don't see what they should be in the training set. You see what the inputs are, you see what the output should be, but the things in the hidden layer are not seen in the training set. So that kind of explains the name hidden layer. It just means you don't see it in the training set. Let's introduce a bit more notation. Whereas previously we were using the vector x to denote the input features, an alternative notation for the values of the input features will be a superscript square bracket 0. And the term a also stands for activations, and it refers to the values that different layers of the neural network are passing on to the subsequent layers. So the input layer passes on the value x to the hidden layer, so we're going to call the activations of the input layer a superscript 0. The next layer, the hidden layer, will in turn generate some set of activations which I'm going to write as a superscript square bracket 1. So in particular, this first unit or this first node will generate the value a superscript square bracket 1 subscript 1. This second node will generate a value now with a subscript 2, and so on. And so a superscript square bracket 1, this is a 4-dimensional vector, or if you want in Python, I guess it's a 4x1 matrix or 4-column vector, which looks like this. And it's 4-dimensional because in this case we have 4 nodes or 4 units or 4 hidden units in this hidden layer. Then finally, the output layer will generate some value a2, which is just a real number, and so y hat is going to take on the value of a2. So this is analogous to how in logistic regression we had y hat equals a, and in logistic regression we only had that one output layer, so we didn't use the superscript square brackets. But with a neural network, we're now going to use the superscript square bracket to explicitly indicate which layer it came from. One funny thing about notational conventions in neural networks is that this network that you're seeing here is called a 2-layer neural network. And the reason is that when we count layers in neural networks, we don't count the input layer. So the hidden layer is layer 1 and the output layer is layer 2. In our notational convention, we're calling the input layer layer 0. So technically, maybe there are 3 layers in this neural network because there's the input layer, the hidden layer, and the output layer. But in conventional usage, if you read research papers and elsewhere in the course, you see people refer to this particular neural network as a 2-layer neural network because we don't count the input layer as an official layer. Finally, something that we'll get to later is that the hidden layer and the output layers will have parameters associated with it. So the hidden layer will have associated with it parameters W and B, and I'm going to write superscript square bracket 1 to indicate that these are parameters associated with layer 1, with the hidden layer. We'll see later that W will be a 4 by 3 matrix and B will be a 4 by 1 vector in this example, where the first coordinate 4 comes from the fact that we have 4 nodes or 4 hidden units in the layer, and 3 comes from the fact that we have 3 input features. We'll talk later about the dimensions of these matrices, and it might make more sense at that time. But then similarly, the output layer has associated with it also parameters W superscript square bracket 2 and B superscript square bracket 2, and it turns out the dimensions of these are 1 by 4 and 1 by 1. And these 1 by 4 is because the hidden layer has 4 hidden units, the output layer has just 1 unit. But again, we'll go over the dimensions of these matrices and vectors in a later video. So you've just seen what a two-layer neural network looks like. That is a neural network with one hidden layer. In the next video, let's go deeper into exactly what this neural network is computing. That is, how this neural network inputs X and goes all the way to computing its output Y hat. In the last video, you saw what a single hidden layer neural network looks like. In this video, let's go through the details of exactly how this neural network computes its outputs. What you see is that it's like logistic regression, but repeated a lot of times. Let's take a look. So this is what a two-layer neural network looks like. Let's go more deeply into exactly what this neural network computes. Now, we've said before that logistic regression, the circle in logistic regression really represents two steps of computation. First, you compute Z as follows, and then second, you compute the activation as a sigmoid function of Z. So a neural network just does this a lot more times. Let's start by focusing on just one of the nodes in the hidden layer. Let's look at the first node in the hidden layer. So I've grayed out the other nodes for now. So similar to logistic regression on the left, this node in the hidden layer does two steps of computation, right? The first step, and think of as the left half of this node, it computes Z equals W transpose X plus B. And the notation we'll use is these are all quantities associated with the first hidden layer, so that's why we have a bunch of square brackets there. And this is the first node in the hidden layer, so that's why we'll have a subscript 1 over there. So first it does that, and then the second step is it computes A11 equals sigmoid of Z11. Like so. So for both Z and A, the notational convention is that A, L, I, the L here in superscript square brackets refers to the layer number, and the I subscript here refers to the node in that layer. So the node we've been looking at is layer 1, that is the hidden layer node 1, so that's why the superscript and subscripts were both 1, 1. So that little circle, that first node in the neural network, represents carrying out these two steps of computation. Now let's look at the second node in the neural network, or the second node in the hidden layer of the neural network. Similar to the logistic regression unit on the left, this little circle represents two steps of computation. The first step is it computes Z, this is still layer 1, but now it's the second node, equals W transpose X plus B, 1, 2, and then A, 1, 2 equals sigmoid of Z, 1, 2. And again, feel free to pause the video if you want, but you can double check that the superscript and subscript notation is consistent with what we had written here above in purple. So we've talked through the first two hidden units in the neural network. Hidden units 3 and 4 also represent similar computations. So now let me take this pair of equations and this pair of equations and let's copy them to the next slide. So here's our neural network, and here's the first and here's the second equations that were worked out previously for the first and the second hidden units. If you then go through and write out the corresponding equations for the third and fourth hidden units, you get the following. And so let's make sure this notation is clear. This is the vector W11, this is a vector transpose times X. Okay, so that's what the superscript T there represents. This is a vector transpose. Now, as you might have guessed, if you're actually implementing a neural network, doing this with a for loop seems really inefficient. So what we're going to do is take these four equations and vectorized. So we're going to start by showing how to compute z as a vector. It turns out you could do it as follows. Let me take these w's and stack them into a matrix. Then you have w11 transpose, so that's a row vector. Oh, this is a column vector transpose, gives you a row vector. Then w12 transpose, w13 transpose, w14 transpose. And so this, by stacking those 4 w vectors together, you end up with a matrix. So another way to think of this is that we have 4 logistic regression units there, and each of the logistic regression units has a corresponding parameter vector w, and by stacking those 4 vectors together, you end up with this 4 by 3 matrix. So if you then take this matrix and multiply it by your input features x1, x2, x3, you end up with, by how matrix multiplication works, you end up with w11 transpose x, w21 transpose x, w31 transpose x, w41 transpose x. And then let's not forget the b's. So we now add to this a vector b11, b12, b13, b14. So that's basically this. Then this gives b11, b12, b13, b14. And so you see that each of the 4 rows of this outcome correspond exactly to each of these 4 rows, to each of these 4 quantities that we had above. So in other words, we've just shown that this thing is therefore equal to z11, z12, z13, z14, right, as defined here. And maybe not surprisingly, we're going to call this whole thing the vector z1, which is taken by stacking up these individuals of z's into a column vector. When we're vectorizing, one of the rules of thumb that might help you navigate this is that when we have different nodes in a layer, we'll stack them vertically. So that's why when you had z11 through z14, those corresponded to 4 different nodes in the hidden layer. And so we stacked these 4 numbers vertically to form the vector z1. And to use one more piece of notation, this 4 by 3 matrix here, which we obtained by stacking the lowercase, w11, w12, and so on, we're going to call this matrix W capital 1. And similarly, this vector we're going to call B superscript 1 square bracket. And so this is a 4 by 1 vector. So now we've computed Z using this vector matrix notation. The last thing we need to do is also compute these values of A. And so probably won't surprise you to see that we're going to define A1 as just stacking together those activation values, A11 through A14. So just take these 4 values and stack them together in a vector called A1, and this is going to be sigmoid of Z1, where this now has been implementation of the sigmoid function that takes in the 4 elements of Z and applies the sigmoid function elements-wise to it. So just to recap, we've figured out that Z1 is equal to W1 times the vector X plus the vector B1, and A1 is sigmoid times Z1. Let's just copy this to the next slide. And what we see is that for the first layer of the neural network, given an input X, we have that Z1 is equal to W1 times X plus B1, and A1 is sigmoid of Z1. And the dimensions of this are 4 by 1 equals, this was a 4 by 3 matrix times a 3 by 1 vector plus a 4 by 1 vector B. And this is 4 by 1, same dimension as Z. And remember that we said X is equal to A0, right? Just like Y hat is also equal to A2. So if you want, you can actually take this X and replace it with A0, since A0 is, if you want, is an alias for the vector of input features X. Now, through a similar derivation, you can figure out that the representation for the next layer can also be written similarly, where what the output layer does is it has associated with it set of parameters W2 and B2. So W2 in this case is going to be a 1 by 4 matrix, and B2 is just a real number as 1 by 1. And so Z2 is going to be a real number. I'm just write as a 1 by 1 matrix. It's going to be a 1 by 4 thing times A was 4 by 1 plus B2 is 1 by 1. And so this gives you just a real number. And if you think of this last output unit as just being analogous to logistic regression, which had parameters W and B, W really plays an analogous role to W2 transpose, so W2 is really W transpose, and B is equal to B2, right? So if we were to, cover up the left of this network and ignore all that for now, then this last output unit is a lot like logistic regression, except that instead of writing the parameters as W and B, we're writing them as W2 and B2 with dimensions 1 by 4 and 1 by 1. So just to recap, for logistic regression, to implement the output or to implement a prediction, you would compute Z equals W transpose X plus B, and A, or Y hat equals A, equals sigmoid of Z. When you have a neural network with one hidden layer, what you need to implement to compute this output is just these four equations. And you can think of this as a vectorized implementation of computing the output of first these four logistic regression units in the hidden layer, that's what this does, and then of this logistic regression in the output layer, which is what this does. I hope this description made sense, but the takeaway is to compute the output of this neural network, all you need is those 4 lines of code. So now you've seen how, given a single input feature vector X, you can, with 4 lines of code, compute the output of this neural network. Similar to what we did for logistic regression, we'll also want to vectorize across multiple training examples. And we'll see that by stacking up training examples in different columns in the matrix, with just a slight modification to this, you also, similar to what you saw in logistic regression, be able to compute the output of this neural network not just on one example at a time, but on your, say, your entire training set at a time. So let's see the details of that in the next video. In the last video, you saw how to compute the prediction on a neural network given a single training example. In this video, you see how to vectorize across multiple training examples. And the outcome will be quite similar to what you saw for logistic regression, where by stacking up different training examples in different columns of a matrix, you'll be able to take the equations you had from the previous video and with very little modification, change them to make the neural network compute the outputs on all the examples pretty much all at the same time. So let's see the details of how to do that. These were the 4 equations we had from the previous video of how you compute Z1, A1, Z2, and A2. And they tell you how, given an input feature vector X, you can use them to generate A2 equals Y hat for a single training example. Now, if you have M training examples, you need to repeat this process for, say, the first training example, X superscript round brackets 1, to compute Y hat 1, that's the prediction on your first training example. Then X2, use that to generate prediction Y hat 2, and so on down to XM to generate a prediction Y hat M. And so in order to write this with the activation function notation as well, I'm going to write this as A2 square bracket round bracket 1. And this is A2, 2, and A2M. So this notation, A square bracket 2 round bracket I, the round bracket I refers to training example I, and the square bracket 2 refers to layer 2. Okay, so that's how the square bracket and the round bracket indices work. And so this suggests that if you have an unvectorized implementation and want to compute the predictions for all your training examples, you need to do for I equals 1 to M, then basically implement these 4 equations, right? You need, I guess, Z1I equals W1 XI plus B1, A1I equals sigmoid of Z1I, Z2I equals W2 A1I plus B2, and A2I equals sigmoid of Z2I, right? So it's basically, these 4 equations on top, but adding the superscript round bracket I to all the variables that depend on the training example. So adding the superscript round bracket I to X, Z, and A if you want to compute all the outputs on your M training examples. what we like to do is vectorize this whole computation so as to get rid of this for loop. And by the way, in case it seems like I'm getting a lot of nitty-gritty linear algebra, it turns out that being able to implement this correctly is important in the deep learning era. And we actually chose the notation very carefully for this class to make these vectorization steps as easy as possible. So I hope that going through this nitty-gritty will actually help you to more quickly get correct implementations of these algorithms working. Alright, so let me just copy this whole block of code to the next slide, and then we'll see how to vectorize this. So here's what we had from the previous slide with the for loop going over all m training examples. So recall that we defined the matrix X to be equal to our training examples stacked up in these columns like so. So take the training examples, stack them in columns. So this becomes a n, or maybe nx by m dimensional matrix. I'm just going to give away the punchline and tell you what you need to implement in order to have a vectorized implementation of this for loop. Turns out what you need to do is compute capital Z1 equals W1 x plus B1, capital A1 equals sigmoid of Z1, then capital Z2 equals W2 times A1 plus B2, and then A2 equals sigmoid of Z2. So if you want, the analogy is that we went from lowercase vector x's to this capital case X matrix by stacking up the lowercase x's in different columns. If you do the same thing for the z's, so for example, if you take z1 1, z1 2, and so on, and these are all column vectors up to z1 m, right? So that's this first quantity, but all m of them, and stack them in columns, then this gives you the matrix Z1. And similarly, if you look at, say, this quantity, you can take A1, 1, A1, 2, and so on in A1, M, and stack them up in columns, then this, just as we went from lowercase x to capital case X and lowercase z to capital case Z, this goes from the lowercase a, which are vectors, to this capital A1, that's over there. And similarly for Z2 and A2. Right? They're also obtained by taking these vectors and stacking them horizontally, and taking these vectors and stacking them horizontally in order to get capital Z2 and capital A2. One other property of this notation that might help you to think about it is that these matrices, say Z and A, horizontally we're going to index across training examples. So that's why the horizontal index corresponds to different training examples. And you sweep from left to right, you're scanning through the training set. And vertically, this vertical index corresponds to different nodes in the neural network. So, for example, this node, this value at the top leftmost corner of the matrix corresponds to the activation of the first hidden unit on the first training example. One value down corresponds to the activation in the second hidden unit on the first training example, then the third hidden unit on the first training example, and so on. So as you scan down, this is indexing into the hidden unit number. Whereas if you move horizontally, then you're going from the first hidden unit in the first training example to now the first hidden unit in the second training example, the third training example, and so on until this node here corresponds to the activation of the first hidden unit in the final training example, in the M training example. Okay, so the horizontally, the matrix A goes over different training examples. And vertically, the different indices in the matrix A corresponds to different hidden units. And a similar intuition holds true for the matrix Z as well as for X, where horizontally it corresponds to different training examples, and vertically it corresponds to different features, different input features, which are really different nodes in the input layer of the neural network. So with these equations, you now know how to implement a neural network with vectorization, that is vectorization across multiple examples. In the next video, I want to show you a bit more justification about why this is a correct implementation of this type of vectorization. It turns out the justification will be similar to what you had seen for logistic regression. Let's go on to the next video. In the previous video, we saw how with your training examples stacked up horizontally in the matrix X, you can derive a vectorized implementation of forward propagation for your neural network. Let's give a bit more justification for why the equations we wrote down is a correct implementation of vectorizing across multiple examples. So let's go through part of the forward propagation calculation for a few examples. Let's say that for the first training example, you end up computing this x1 plus b1, and then for the second training example, you end up computing this 1x2 plus b1, and then for the third training example, you end up computing this x3 plus b1. So just to simplify the explanation on this slide, I'm going to ignore b. So let's just say, to simplify this justification a little bit, that b is equal to 0. But the argument I'm going to lay out will work with just a little bit of a change, even when b is non-zero. But let's just simplify the description on this slide a bit. Now, W1 is going to be some matrix, right? So I have some number of rows in this matrix. So if you look at this calculation x1, what you have is that W1 times x1 gives you some column vector, which I'm going to draw like this. And similarly, if you look at this vector x2, you have that W1 times x2 gives some other column vector, right? And that's gives you this, I guess, z12. And finally, if you look at x3, you have W1 times x3 gives you some third column vector. That's this z13. So now, if you consider the training set capital X, which we formed by stacking together all of our training examples. So the matrix capital X is formed by taking the vector x1 and stacking it vertically with x2, and then also x3. This is if we have only 3 training examples. If you have more, it'll keep stacking horizontally like that. But if you now take this matrix X and multiply it by W, then you end up with, if you think about how matrix multiplication works, you end up with the first column being these same values that I had drawn up there in purple. The second column will be those same 4 values, and the third column will be those orange values, whatever they turn out to be. But of course, this is just equal to z11 expressed as a column vector, followed by z12 expressed as a column vector, followed by z13 also expressed as a column vector. And this is if you have 3 training examples. If you have more examples, then there'll be more columns. And so this is just our matrix capital Z1. So I hope this gives a justification for why, when we had previously W1 times xi equals Z1i, when we're looking at a single training example at a time, when you took the different training examples and stacked them up in different columns, then the corresponding result is that you end up with the z's also stacked up in columns. And I won't show, but you can convince yourself if you want that with Python broadcasting, if you add back in these values of b, that the values are still correct. And what actually ends up happening is you end up, with Python broadcasting, you end up adding bi individually to each of the columns of this matrix. So on this slide, I've only justified that z1 equals w1 x plus b1 is a correct vectorization of the first step of the 4 steps that we had on the previous slide. But it turns out that a similar analysis allows you to show that the other steps also work out using a very similar logic, where if you stack the inputs in columns, then after the equation you get the corresponding outputs also stacked up in columns. Finally, let's just recap everything we talked about in this video. If this is your neural network, we said that this is what you need to do if you were to implement forward propagation, one training example at a time, going from I equals 1 through m. And then we said, let's stack up the training examples in columns like so. And for each of these values, z1, a1, z2, a2, let's stack up the corresponding columns as follows. So this is an example for a1, but this is true for z1, a1, z2, and a2. Then what we showed on the previous slide was that this line allows you to vectorize this across all m examples at the same time. And it turns out with a similar reasoning, you can show that all of the other lines are correct vectorizations of all 4 of these lines of code. And just as a reminder, because x is also equal to a0, because remember that the input feature vector x was equal to a0. So xi equals a0i, right? Then there's actually a certain symmetry to these equations, where this first equation can also be written z1 equals w1 a0 plus b1. And so you see that this pair of equations and this pair of equations actually look very similar, but just with all of the indices advanced by 1. So this kind of shows that the different layers of a neural network are, roughly doing the same thing, or just doing the same computation over and over. And here we have a 2-layer neural network. When we go to a much deeper neural network in next week's videos, you see that even deeper neural networks are basically taking these 2 steps and just doing them even more times than you're seeing here. So that's how you can vectorize your neural network across multiple training examples. Next, we've so far been using the sigmoid function throughout our neural networks. Turns out that's actually not the best choice. In the next video, let's delve a little bit further into how you can use different what's called activation functions, of which the sigmoid function is just one possible choice. When you build your neural network, one of the choices you get to make is what activation function to use in the hidden layers as well as at the output unit of your neural network. So far, we've just been using the sigmoid activation function, but sometimes other choices can work much better. Let's take a look at some of the options. In the forward propagation steps for the neural network, we had these 2 steps where we use the sigmoid function here. So that sigmoid is called an activation function. And here's the familiar sigmoid function, a equals 1 over 1 plus e to the negative z. So in the more general case, we can have a different function, g of z, which I'm going to write here, where g could be a nonlinear function that may not be the sigmoid function. So for example, the sigmoid function goes between 0 and 1. An activation function that almost always works better than the sigmoid function is the tanh function, or the hyperbolic tangent function. So this is z, this is a equals tan h of z, and this goes between +1 and -1. The formula for the tan h function is e to the z minus e to the negative z over their sum. and is actually mathematically a shifted version of the sigmoid function. So is a sigmoid function just like that, but shifted so that it now crosses a 0, 0 point and rescales, so it goes between -1 and +1. And it turns out that for hidden units, if you let the function g of z be equal to tan h of z, this almost always works better than the sigmoid function, because with values between +1 and -1, the mean of the activations that come out of your hidden layer are closer to having a 0 mean. And so just as sometimes when you train a learning algorithm, you might center the data and have your data have 0 mean, using a tan h instead of a sigmoid function kind of has the effect of centering your data so that the mean of your data is closer to 0 rather than maybe 0.5, and this actually makes learning for the next layer a little bit easier. We'll say more about this in the second course when we talk about optimization algorithms as well. But one takeaway is that I pretty much never use the sigmoid activation function anymore. The tan h function is almost always strictly superior. The one exception is for the output layer, because if y is either 0 or 1, then it makes sense for y hat to be a number that you want to output that's between 0 and 1 rather than between -1 and 1. So the one exception where I would use the sigmoid activation function is when you're using binary classification, in which case you might use the sigmoid activation function for the output layer. So g of z2 here is equal to sigma of z2. And so what you see in this example is where you might have a tan h activation function for the hidden layer and sigmoid for the output layer. So the activation functions can be different for different layers. And sometimes to denote that the activation functions are different for different layers, we might use these square bracket superscripts as well to indicate that g of square bracket 1 may be different than g of square bracket 2, right? And again, square bracket 1 superscript refers to this layer, and superscript square bracket 2 refers to the output layer. Now, one of the downsides of both the sigmoid function and the tan h function is that if z is either very large or very small, then the gradient or the derivative or the slope of this function becomes very small. So if z is very large or z is very small, the slope of the function ends up being close to 0, and so this can slow down gradient descent. So one other choice that is very popular in machine learning is what's called the rectified linear unit. So the ReLU function looks like this, and the formula is a equals max of 0 comma z. So the derivative is 1 so long as z is positive, and the derivative or the slope is 0 when z is negative. If you're implementing this, technically the derivative when z is exactly 0 is not well defined, but when you implement this in the computer, the odds that you get exactly z equals 0.00000000000 is very small, so you don't need to worry about it. In practice, you could pretend the derivative when z is equal to 0. You can pretend it's either 1 or 0, and your code will work just fine. So the fact that it's not differentiable, So here are some rules of thumb for choosing activation functions. If your output is 0, 1 valued, if you're using binary classification, then the sigmoid activation function is a very natural choice for the output layer. And then for all other units, ReLU, or the rectified linear unit, is increasingly the default choice of activation function. So if you're not sure what to use for your hidden layer, I would just use the ReLU activation function. It's what you see most people using these days, although sometimes people also use the tan h activation function. One disadvantage of the ReLU is that the derivative is equal to 0 when z is negative. In practice, this works just fine, but there is another version of the ReLU called the leaky ReLU. We'll give you the formula on the next slide, but instead of it being 0 when z is negative, it just takes a slight slope like so. So this is called the leaky ReLU. This usually works better than the ReLU activation function, although it's just not used as much in practice. Either one should be fine, although if you had to pick one, I usually just use the ReLU. And the advantage of both the ReLU and the leaky ReLU is that for a lot of the space of z, the derivative of the activation function, the slope of the activation function, is very different from 0. And so in practice, using the ReLU activation function, your neural network will often learn much faster than you're using the tanh or the sigmoid activation function. And the main reason is that there's less of this effect of the slope of the function going to 0, which slows down learning. And I know that for half of the range of z, the slope for ReLU is 0, but in practice, enough of your hidden units will have z greater than 0, so learning can still be quite fast for most training examples. So let's just quickly recap the pros and cons of different activation functions. Here's the sigmoid activation function. I would say never use this except for the output layer if you are doing binary classification, or maybe almost never use this. And the reason I almost never use this is because the tanh is pretty much strictly superior. So the tanh activation function is this. And then the default, the most commonly used activation function is the ReLU, which is this. So if you're not sure what else to use this one. And maybe, feel free also to try the leaky ReLU, where might be 0.01z, comma z, right? So a is the max of 0.01 times z and z. So that gives you this bend in the function. And you might say, why is that constant 0.01? Well, you can also make that another parameter of the learning algorithm. And some people say that works even better, but I hardly see people do that. But if you feel like trying it in your application, please feel free to do so. And you can just see how it works and how well it works and stick with it if it gives you a good result. So I hope that gives you a sense of some of the choices of activation functions you can use in your neural network. One of the themes we'll see in deep learning is that you often have a lot of different choices in how you build your neural network, ranging from number of hidden units to the choice of activation function, to how you initialize the weights, which we'll see later, a lot of choices like that. And it turns out that it's sometimes difficult to get good guidelines for exactly what will work best for your problem. So throughout these few courses, I'll keep on giving you a sense of what I see in the industry in terms of what's more or less popular. But for your application, with your application's idiosyncrasies, it's actually very difficult to know in advance exactly what will work best. So a common piece of advice would be, if you're not sure which one of these activation functions work best, try them all and evaluate on like a holdout validation set or like a development set, which we'll talk about later, and see which one works better and then go with that. And I think that by testing these different choices for your application, you'd be better at future-proofing your neural network architecture against the idiosyncrasies of your problem as well as evolutions of the algorithms, rather than if I were to tell you always use a ReLU activation and don't use anything else, that just may or may not apply for whatever problem you end up working on, either in the near future or in the distant future. All right, so that was a choice of activation functions, and you've seen the most popular activation functions. There's one other question that sometimes we can ask, which is, why do you even need to use an activation function at all? Why not just do away with that? So let's talk about that in the next video, and where you see why neural networks do need some sort of nonlinear activation function. Why does your neural network need a nonlinear activation function? Turns out that for your neural network to compute interesting functions, you do need to pick a nonlinear activation function. Let's see why. So here's the 4 prop equations for the neural network. Why don't we just get rid of this? Get rid of the function g and set a1 equals z1. Or alternatively, you could say that g of z is equal to z, right? Sometimes this is called the linear activation function. Maybe a better name for it would be the identity activation function, because it just outputs whatever was input. For the purpose of this, what if A2 was just equal to Z2? It turns out if you do this, then this model is just computing y, or y hat, as a linear function of your input features, x. To take the first two equations, if you have that A1 is equal to Z1 is equal to W1 x plus b, and if then A2 is equal to Z2 is equal to W2 A1 plus b, then if you take this definition of A1 and plug it in there, you find that A2 is equal to W2 times W1x plus B1. Let's clean that up a bit. Right, so this is A1 plus B2, and so this simplifies to W2 W1x plus W2 B1 plus B2. So this is just, let's call this W prime B prime. So this is just equal to W prime x plus B prime. If you were to use linear activation functions, or we could also call them identity activation functions, then the neural network is just outputting a linear function of the input. And we'll talk about deep networks later, neural networks with many layers, many hidden layers. And it turns out that if you use a linear activation function, or alternatively, if you don't have an activation function, then no matter how many layers your neural network has, all it's doing is just computing a linear activation function. So you might as well not have any hidden layers. Some of the cases that I'll briefly mention, it turns out that if you have a linear activation function here and a sigmoid function here, then this model is no more expressive than standard logistic regression without any hidden layer. So I won't bother to prove that, but you could try to do so if you want. But the take home is that a linear hidden layer is more or less useless, because the composition of two linear functions is itself a linear function. So unless you throw a nonlinearity in there, then you're not computing more interesting functions even as you go deeper in the network. There is just one place where you might use a linear activation function, g of z equals z, and that's if you are doing machine learning on a regression problem. So if y is a real number. So for example, if you're trying to predict housing prices, so y is not 0 or 1, but is a real number, anywhere from, I don't know, $0 is the price of a house up to however expensive, right, houses get. I guess maybe houses can be, potentially millions of dollars. So however much houses cost in your data set. But if y takes on these real values, then it might be okay to have a linear activation function here so that your output y hat is also a real number going anywhere from minus infinity to plus infinity. But then the hidden units should not use linear activation functions. They could use ReLU or tanh, or leaky ReLU, or maybe something else. So the one place you might use a linear activation function is usually in the output layer. But other than that, using a linear activation function in a hidden layer, except for some very special circumstances relating to compression that I won't want to talk about, using a linear activation function is extremely rare. Oh, and of course, if you're actually predicting housing prices, as we saw in the week 1 video, because housing prices are all non-negative, perhaps even then, you could use a ReLU activation function so that your outputs y hat are all greater than or equal to 0. So I hope that gives you a sense for why having a nonlinear activation function is a critical part of neural networks. Next, we're going to start to talk about gradient descent. And to do that, to set up for our discussion for gradient descent, In the next video, I want to show you how to estimate or how to compute the slope or the derivatives of individual activation functions. So let's go on to the next video. When you implement backpropagation for your neural network, you need to really compute the slope or the derivative of the activation functions. So let's take a look at our choices of activation functions and how you can compute the slope of these functions. Here's the familiar sigmoid activation function. And so for any given value of z, maybe this value of z, this function will have some slope or some derivative corresponding to, if you draw a little line there, the height over width of this little triangle here. So if g of z is the sigmoid function, then the slope of the function is d dz g of z. And so we know from calculus that this is the slope of g of x at z. And if you are familiar with calculus and know how to take derivatives, if you take the derivative of the sigmoid function, it is possible to show that it is equal to this formula. And again, I'm not going to do the calculus steps, but if you're familiar with calculus, feel free to pause the video and try to prove this yourself. And so this is equal to just g of z times 1 minus g of z. So let's just sanity check that this expression makes sense. First, if z is very large, let's say z is equal to 10, then g of z will be close to 1. And so the formula we have on the left tells us that d dz g of z does be close to g of z, which is equal to 1 times 1 minus 1, which is therefore very close to 0. And this is indeed correct because when z is very large, the slope is close to 0. Conversely, if z is equal to minus 10, so say it's way out there, then g of z is close to 0. So the formula on the left tells us d dz g of z will be close to g of z, which is 0, times 1 minus 0. And so this is also very close to 0, which is correct. Finally, if z is equal to 0, then g of z is equal to 1/2. That's a sigmoid function right here. And so the derivative is equal to 1/2 times 1 minus 1/2, which is equal to 1/4. And that actually turns out to be the correct value of the derivative or the slope of this function when z is equal to 0. Finally, just to introduce one more piece of notation, sometimes instead of writing this thing, the shorthand for the derivative is g prime of z. So g prime of z in calculus, the little dash on top is called prime. But so g prime of z is a shorthand in calculus for the derivative of the function of g with respect to the input variable z. And then in a neural network, we have a equals g of z, right, equals this. Then this formula also simplifies to a times 1 minus a. So sometimes in implementation, you might see something like g prime of z equals a times 1 minus a. And that just refers to, the observation that g prime, which just means the derivative, is equal to this over here. And the advantage of this formula is that if you've already computed the value for a, then by using this expression, you can very quickly compute the value for the slope for g prime as well. All right, so that was the sigmoid activation function. Let's now look at the tanh activation function. Similar to what we had previously, the definition of d dz g of z is the slope of g of z at a particular point of z. And if you look at the formula for the hyperbolic tangent function, and if you know calculus, you can take derivatives and show that this simplifies to this formula. And using the shorthand we had previously, we're going to call this g prime of z again. So if you want, you can sanity check that this formula makes sense. So for example, if z is equal to 10, tan h of z will be very close to 1. This goes from plus 1 to minus 1. And then g prime of z, according to this formula, will be about 1 minus 1 squared. So derivative will be close to 0. So that was if z is very large, the slope is close to 0. Conversely, if z is very small, say z is equal to minus 10, then tan h of z will be close to minus 1, and so g prime of z will be close to 1 minus negative 1 squared, so it's close to 1 minus 1, which is also close to 0. And then finally, if z equals to 0, then tan h of z is equal to 0, and then the slope is actually equal to 1, which is actually the slope when z is equal to 0. So just to summarize, if a is equal to g of z, so if a is equal to this tan h of z, then the derivative g prime of z is equal to 1 minus a squared. So once again, if you've already computed the value of a, you can use this formula to very quickly compute the derivative as well. Finally, here's how you compute the derivatives for the ReLU and leaky-ReLU activation functions. For the ReLU, g of z is equal to max of 0, comma z. So the derivative is equal to, turns out to be 0 if z is less than 0, and 1 if z is greater than 0, and is actually undefined, technically undefined if z is equal to exactly 0. But if you're implementing this in software, it might not be 100% mathematically correct, but it'll work just fine if z is exactly equal to 0, if you set the derivative to be equal to 1. Or if you set it to be 0, it kind of doesn't matter. If you're on exponent optimization, technically g prime then becomes what's called a subgradient of the activation function g of z, which is why gradient descent still works. But you can think of it as that the chance of z being, 0. Exactly 0.00000 is so small that it almost doesn't matter what you set the derivative to be equal to when z is equal to 0. So in practice, this is what people implement for the derivative of z. And finally, if you are training a neural network with the leaky-ReLU activation function, then g of z is going to be max of, say, 0.01z, comma z. And so g prime of z is equal to 0.01 if z is less than 0, and 1 if z is greater than 0. And once again, the gradient is technically not defined when z is exactly equal to 0, but if you implement a piece of code that sets the derivative or that sets g prime to either 0.01 or to 1, either way, it doesn't really matter. When z is exactly 0, your code will work just fine. So armed with these formulas, you should be able to compute the slopes or the derivatives of your activation functions. Now that you have this building block, you're ready to see how to implement gradient descent for your neural network. Let's go on to the next video to see that. Alright, I think this will be an exciting video. In this video, you'll see how to implement gradient descent for your neural network with one hidden layer. In this video, I'm going to just give you the equations you need to implement in order to get backpropagation or to get gradient descent working. And then in the video after this one, I'll give some more intuition about why these particular equations are the accurate equations or the correct equations for computing the gradients you need for your neural network. So your neural network with a single hidden layer for now will have parameters w1, b1, w2, and b2. And so as a reminder, if you have an x, or alternatively n0 input features and n1 hidden units and n2 output units, in our example, so far I've only had n2 equals 1, then the matrix w1 will be n1 by n0. b1 will be an n1 dimensional vector, so you can write that as a n1 by 1 dimensional matrix, really a column vector. The dimensions of w2 will be n2 by n1, and the dimension of b2 will be n2 by 1. Right, where again, so far we've only seen examples where n2 is equal to 1, where you have just a single hidden unit. So you also have a cost function for your neural network, and for now I'm just going to assume that you're doing binary classification. So in that case, the cost of your parameters as follows is going to be 1 over m of the average of that loss function. And so L here is the loss when your neural network predicts y hat, right? This is really A2 when the ground truth label is equal to y. And if you're doing binary classification, the loss function can be exactly what you use for logistic regression earlier. So to train the parameters of your algorithm, you need to perform gradient descent. When training a neural network, it's important to initialize the parameters randomly rather than to all zeros. We'll say later why that's the case, but after initializing the parameters to something, right, each loop of gradient descent would compute the predictions. So you basically compute y hat I for I equals 1 through m, say, and then you need to compute the derivatives. So you need to compute dw1, and that's basically the derivative of the cost function with respect to the parameter w1. You need to compute another variable, which we're going to call db1, which is the derivative or the slope of your cost function with respect to the variable b1, and so on. Similarly for the other parameters w2 and b2. And then finally, the gradient descent update would be to update w1 as w1 minus alpha, the learning rate, times d w1. b1 gets updated as b1 minus the learning rate times d b1. And similarly for w2 and b2. And sometimes I use colon equals and sometimes equals, as either notation works fine. And so this would be one iteration of gradient descent, and then you repeat this some number of times until your parameters look like they're converging. So in previous videos, we talked about how to compute the predictions, how to compute the outputs, and we saw how to do that in a vectorized way as well. So the key is to know how to compute these partial derivative terms, the dw1, db1, as well as the derivatives dw2 and db2. So what I'd like to do is just give you the equations you need in order to compute these derivatives. And I'll defer to the next video, which is an optional video, to go greater into depth about how we came up with those formulas. So let me just summarize again the equations for forward propagation. So you have z1 equals w1x plus b1, and then a1 equals the activation function in that layer applied element-wise to z1, and then z2 equals w2 a1 plus b2, and then finally this is all vectorized across your training set, right? A2 is equal to g2 of z2. But again, for now, if we assume you're doing binary classification, then this activation function really should be the sigmoid function. So I can just fill that in here. So that's the forward propagation, or the left to right forward computation for your neural network. Next, let's compute the derivatives. So this is the back propagation step. I'm going to compute dz2 equals a2 minus the ground truth y. And just as a reminder, all this is vectorized across examples. So the matrix Y is this 1 by m matrix that lists all of your m examples stacked horizontally. Then it turns out dw2 is equal to this. In fact, these first three equations are very similar to gradient descent for logistic regression. Comma, x is equals 1, comma, keep dims equals true. And just a little detail, this np.sum is a Python NumPy command for summing across one dimension of a matrix, in this case, summing horizontally. And what keep dims does is it prevents Python from outputting one of those funny rank 1 arrays, right, where the dimensions was, n comma. So by having keep dims equals true, this ensures that Python outputs for db2 a vector that is n by 1. In fact, technically this will be, I guess, n2 by 1. In this case, it's just a 1 by 1 number, so maybe it doesn't matter but later on we'll see when it really matters. So far what we've done is very similar to logistic regression, but now as you continue to run backpropagation, you would compute this. So dz2 times g1 prime of z1. So this quantity g1 prime is the derivative of whatever was the activation function you use for the hidden layer. And for the output layer, I assume that you're doing binary classification with the sigmoid function. So that's already baked into that formula for dz2. And this times is an element-wise product. So this here is going to be an n1 by m matrix. And this here, this element-wise derivative thing is also going to be an n1 by m matrix, and so this times there is an element-wise product of two matrices. Then finally, dw1 is equal to that, and db1 is equal to this np.sum dz1 axis equals 1, keep dims equals true. So whereas previously the keep dims maybe mattered less if n2 is equal to 1, so this is just a 1 by 1 thing, it's just a real number. Here, db1 will be a n1 by 1 vector, and so you want Python, you want np.sum to output something of this dimension rather than a funny rank 1 array of that dimension, which could end up messing up some of your later calculations. The other way would be to not have to keep dim parameters, but to explicitly call, reshape, to reshape the output of np.sum into this dimension, which you would like db to have. So that was forward propagation in, 4 equations, and back propagation in, 6 equations. I know I just wrote down these equations, but in the next optional video, let's go over some intuitions for how the 6 equations for the backpropagation algorithm were derived. Please feel free to watch that or not, but either way, if you implement these algorithms, you will have a correct implementation of forward prop and back prop, and you'll be able to compute the derivatives you need in order to apply gradient descent to learn the parameters of your neural network. It is possible to implement this algorithm and get it to work without deeply understanding the calculus. A lot of successful deep learning practitioners do so, but if you want, you can also watch the next video just to get a bit more intuition about the derivation of these equations. In the last video, you saw the equations for backpropagation. In this video, let's go over some intuition using the computation graph for how those equations were derived. This video is completely optional, so feel free to watch it or not. You should be able to do the homeworks either way. So recall that when we talked about logistic regression, we had this forward pass where we would compute z, then a, and then a loss. And then to take derivatives, we had this backward pass where we could first compute dA, and then go on to compute dz, and then go on to compute dw and db. So the definition for the loss was L of a comma y equals negative y log a minus 1 minus y times log 1 minus a. So if you're familiar with calculus and you take the derivative of this with respect to a, that would give you the formula for dA. So dA is equal to that. And if you actually figure out the calculus, you could show that this is y over a, negative y over a, plus 1 minus y over 1 minus a. And you just kind of derive that from calculus by taking derivatives of this. It turns out when you take another step backwards to compute dz, we then worked out that dz is equal to a minus y. I didn't explain why previously, but it turns out that from the chain rule of calculus, dz is equal to dA times g prime of z, where here g of z equals sigmoid of z is our activation function for this output unit in logistic regression, right? So just remember, this is still logistic regression where we have x1, x2, x3, and then just one sigmoid unit, and then that gives us a, or gives us y hat. So here, the activation function was a sigmoid function. And as an aside, only for those of you familiar with the chain rule of calculus, the reason for this is because a is equal to sigmoid of z, and so partial of L with respect to z is equal to partial of L with respect to a times dA dz, but since a is equal to sigmoid of z, this is equal to d dz g of z, right? Or this, which is equal to g prime of z. So that's why this expression, which is dz in our code, is equal to this expression, which is dA in our code, times g prime of z. And so this is just that. So that last derivation would make sense only if you're familiar with calculus, and specifically the chain rule from calculus, but if not, don't worry about it. I'll try to explain the intuition wherever is needed. And then finally, having computed dz for logistic regression, we would compute dw, which it turns out was dz times x, and db, which is just dz when you have a single training example. So that was logistic regression. So what we're going to do when computing backpropagation for a neural network is a calculation a lot like this, but only we'll do it twice, because now we have not x going to an output unit, but x going to a hidden layer, and then going to an output unit. And so instead of this computation being sort of one step as we have here, we'll have, two steps here, right, in this kind of a neural network with two layers. So in this two-layer neural network, that is with an input layer, a hidden layer, and an output layer, remember the steps of a computation. First, you compute z1 using this equation, and then compute a1, and then you compute z2, and notice z2 also depends on the parameters w2 and b2, and then based on z2 you compute a2, and then finally that gives you the loss. So what backpropagation does is it will go backward to compute dA2 and then dZ2, it can go back to compute dW2 and dB2, go back to compute dA1, dZ1, and so on. Okay. Well, we don't need to take derivatives with respect to the input x, since the input x for supervised learning is fixed, so we're not trying to optimize x, so we won't bother to take derivatives, at least for supervised learning with respect to x. And so I'm going to skip explicitly computing dA2. If you want, you can actually compute dA2 and then use that to compute dZ2, but in practice you could collapse both of these steps into one step, so you end up that dZ2 is equal to a2 minus y, same as before. And you have also, I'm going to write dw2 and db2 down here below. You have that dw2 is equal to dz2 times a1 transpose, and db2 equals dz2. So this step is quite similar to for logistic regression, where we had that dw was equal to dz times x, except that now a1 plays the role of x, and there's an extra transpose there because the relationship between the capital matrix W and our individual parameters W was there's a transpose there, right? Because W is equal to a row vector in the case of logistic regression with a single output. dW2 is like that, whereas W here was a column vector, so that's why there's an extra transpose for A1, whereas we didn't for X here for logistic regression. So this completes half of backpropagation. And then again, you can compute dA1 if you wish, although in practice, the computation for dA1 and dz1 are usually collapsed into one step. And so what you'd actually implement is that dz1 is equal to w2 transpose times dz2, and then times an element-wise product of g1 prime of z1. And just to do a check on the dimensions, right? If you have a neural network that looks like this, right? Outputs y. So if you have n0 and x equals n0 input features, n1 hidden units, and n2 so far, and n2, in our case, just one output unit, then the matrix W2 is n2 by n1 dimensional, z2, and therefore dz2 are going to be n2 by 1 dimensional. It's really going to be a 1 by 1 when we're doing binary classification. And z1, and therefore also dz1, are going to be n1 by 1 dimensional. Right? Note that for any variable foo and dfoo always have the same dimension. So that's why w and dw, always have the same dimension. And similarly for b and db and z and dz and so on. So to make sure that the dimensions of this all match up, we have that dz1 is equal to w2 transpose times dz2, and then this is an element-wise product times g1 prime of z1. So matching the dimensions from above, this is going to be n1 by 1 is equal to w2 transpose, we transpose of this. So this is going to be n1 by n2 dimensional. dz2 is going to be n2 by 1 dimensional. And then this is the same dimension as z1, so this is also n1 by 1 dimensional, so element-wise product. So the dimensions do make sense, right? An n1 by 1 dimensional vector can be obtained by an n1 by n2 dimensional matrix times n2 by n1, because the product of these two things gives you an n1 by 1 dimensional matrix. And so this becomes the element-wise product of two n1 by 1 dimensional vectors. And so the dimensions do match up. One tip when implementing backprop, if you just make sure that the dimensions of your matrices match up, so if you think through what are the dimensions of your various matrices, including W1, W2, Z1, Z2, A1, A2, and so on, and just make sure that the dimensions of these matrix operations match up, sometimes that will already eliminate quite a lot of bugs in backprop. Alright, so this gives us dz1, and then finally, just to wrap up, dw1 and db1, we should write them here, I guess, but since I'm running out of space, I'll write them on the right of the slide. dw1 and db1 are given by the following formulas. This is going to be equal to dz1 times x transpose, and this is going to be equal to dz. And you might notice a similarity between these equations and these equations, right? Which is really no coincidence because x plays the role of A0, so x transpose is A0 transpose. So those equations are actually very similar. Alright, so that gives a sense for how backpropagation is derived. And we have 6 key equations here for dz2, dw2, db2, dz1, dw1, and db1. So let me just take these 6 equations and copy them over to the next slide. Here they are. And so far, we've derived backpropagation for if you're training on a single training example at a time. But it should come as no surprise that rather than working on a single example at a time, we would like to vectorize across different training examples. So you remember that for forward propagation, when we're operating on one example at a time, we had equations like this, as well as say A1 equals G1 of Z1. And in order to vectorize, we took, say, the Z's and stack them up in columns like this, onto Z1M, and call this capital Z. And then we found that, by stacking things up in columns and defining the capital uppercase version of these, we then just had Z1 equals W1X plus B, and A1 equals G1 of Z1, right? And we defined the notation very carefully in this course to make sure that stacking examples in the different columns of a matrix makes all this work out. So it turns out that if you go through the math carefully, the same trick also works for backpropagation. So the vectorized equations are as follows. First, if you take these DZs for different training examples and stack them as the different columns of a matrix, and same for this and same for this, then this is the vectorized implementation. And then here's the definition or here's how you can compute dW2. There is this extra 1 over m because the cost function j is this 1 over m of sum from I equals 1 through m of the losses. And so when computing derivatives, we have that extra 1 over m term, just as we did when we were computing the weight updates for logistic regression. And then that's the update you get for dB2. Again, sum of the dz's, and then with a 1 over m. And then dz1 is computed as follows. Once again, this is an element-wise product. Only whereas previously, we saw on the previous slide that this was an n1 by 1 dimensional vector. Now this is a n1 by m dimensional matrix. And both of these are also n1 by m dimensional. And so that's why that asterisk is a element-wise product. Right? And then finally, the remaining two updates perhaps shouldn't look too surprising. So I hope that gives you some intuition for how the backpropagation algorithm is derived. In all of machine learning, I think the derivation of the backpropagation algorithm is actually one of the most complicated pieces of math I've seen. And it requires knowing both linear algebra as well as the derivative of matrices to really derive it from scratch, from first principles. If you are an expert in matrix calculus, using this process, you might be able to derive the algorithm yourself. But I think that there are actually plenty of deep learning practitioners that have seen the derivation at about the level you've seen in this video and are already able to have all the right intuitions and be able to implement this algorithm very effectively. So if you are an expert in calculus, do see if you can derive the whole thing from scratch. It is one of the very hardest pieces of math, one of the very hardest derivations that I've seen in all of machine learning. But either way, if you implement this, this will work, and I think you have enough intuitions to tune it and get it to work. So with that, there's just one last detail I want to share with you before you implement your neural network, which is how to initialize the weights of your neural network. And it turns out that initializing your parameters not to 0, but randomly, turns out to be very important for training your neural network. In the next video, you'll see why. When you train your neural network, it's important to initialize the weights randomly. For logistic regression, it was okay to initialize the weights to 0, but for a neural network, if you initialize the weights, the parameters to all 0 and then apply gradient descent, it won't work. Let's see why. So you have here two input features, so n0 is equal to 2, and two hidden units, so n1 is equal to 2. And so the matrix associated with the hidden layer, or W1, is going to be 2 by 2. Let's say that you initialize it to all zeros, so 0, 0, 0, 0, 2 by 2 matrix. And let's say B1 is also equal to 0, 0. Turns out initializing the bias terms B to 0 is actually okay, but initializing W to all zeros is a problem. So the problem with this form of initialization is that for any example you give it, you will have that A11 and A12 will be equal, right? So this activation and this activation will be the same because both of these hidden units are computing exactly the same function. And then when you compute backpropagation, it turns out that dz11 and dz12 will also be the same, kind of by symmetry, right? Both of these hidden units will initialize the same way. Technically, for what I'm saying, I'm assuming that the outgoing weights are also identical, so that W2 is equal to 0, 0. But if you initialize the neural network this way, then this hidden unit and this hidden unit are completely identical. So they're completely, sometimes you say they're completely symmetric, which just means that they're computing exactly the same function. And by kind of a proof by induction, it turns out that after every single iteration of training, your two hidden units are still computing exactly the same function. So it's possible to show that dW will be a matrix that looks like this, where every row takes on the same value. So when you perform a weight update, when you perform a weight update, W1 gets updated as W1 minus alpha times dW. You find that W1, after every iteration, will have the first row equal to the second row. So it's possible to construct a proof by induction that if you initialize all the weights, all the values of W to 0, then because both hidden units start off computing the same function and both hidden units have the same influence on the output unit, then after one iteration, that same statement is still true. The two hidden units are still symmetric, and therefore by induction, after 2 iterations, 3 iterations, and so on, no matter how long you train the neural network, both hidden units are still computing exactly the same function. And so in this case, there's really no point to having more than one hidden unit because they're all computing the same thing. And of course, for larger neural networks, let's say you have 3 features and maybe a very large number of hidden units, a similar argument works to show that with a neural network like this, because I won't draw on all the edges, if you initialize the weights to 0, then all of your hidden units are symmetric, and no matter how long you run gradient descent, they'll all continue to compute exactly the same function. So that's not helpful because you want the different hidden units to compute different functions. The solution to this is to initialize your parameters randomly. So here's what you do. You can set W1 equals np.random.randn. This generates a Gaussian random variable 2, and then usually you multiply this by a very small number, such as 0.01. So you initialize it to very small random values. And then B, it turns out that B does not have this symmetry problem, what's called the symmetry breaking problem. So it's okay to initialize B to just zeros, because so long as W is initialized randomly, you start off with the different hidden units computing different things, and so you no longer have this symmetry breaking problem. And then similarly for W2, you can initialize that randomly, and B2, you can initialize that to 0. So you might be wondering, where did this constant come from, and why is it 0.01? Why not put the number 100 or 1000? Turns out that we usually prefer to initialize the weights to very, very small random values. Because if you're using a, say, tanh or sigmoid activation function, or if you have a sigmoid, even just at the output layer, if the weights are too large, then when you compute the activation values, remember that Z1 is equal to W1 x plus b, and then A1 is the activation function applied to Z1. So if W is very big, Z will be very big, or at least some values of Z will be either very large or very small. And so in that case, you're more likely to end up at these flat parts of the tanh function or the sigmoid function, where the slope or the gradient is very small, meaning that gradient descent would be very slow, and so learning would be very slow. So just to recap, if W is too large, you're more likely to end up, even at the very start of training, with very large values of Z, which causes your tanh or your sigmoid activation function to be saturated, thus slowing down learning. If you don't have any sigmoid or tanh activation functions throughout your neural network, this is less of an issue, but if you're doing binary classification and your output unit is a sigmoid function, then you just don't want the initial parameters to be too large. So that's why multiplying by 0.01 would be something reasonable to try, or any other small number. And same for W2, right? This can be a random.random. I guess this would be 1 by 2 in this example, times 0.01. Oh, missing a S there. So finally, it turns out that sometimes there can be better constants than 0.01. When you're training a neural network with just one hidden layer, this is a relatively shallow neural network without too many hidden layers, setting it to 0.01 would probably work okay. But when you're training a very, very deep neural network, then you might want to pick a different constant than 0.01. And in next week's material, we'll talk a little bit about how and when you might want to choose a different constant than 0.01. But either way, it will usually end up being a relatively small number. So that's it for this week's videos. You now know how to set up a neural network with a hidden layer, initialize the parameters, make predictions using forward prop, as well as compute derivatives and implement gradient descent using back prop. So with that, you should be able to do the quizzes as well as this week's programming exercises. Best of luck with that. I hope you have fun with the programming exercise, and I look forward to seeing you in the week 4 materials. Welcome to the 4th week of this class. By now, you've seen forward propagation and back propagation in the context of a neural network with a single hidden layer, as well as logistic regression. And you've learned about vectorization and, when it's important, initialize the weights randomly. If you've done the past couple of weeks' homeworks, you've also implemented and seen some of these ideas work for yourself. So by now, you've actually seen most of the ideas you need to implement a deep neural network. What we're going to do in this week is take those ideas and put them together so that you'll be able to implement your own deep neural network. Because this week's programming exercise is longer and just has a bit more work, I'm going to keep the videos for this week shorter so you can get through the videos a little bit more quickly and then have more time to do a significant programming exercise at the end, which I hope will leave you having built a deep neural network that you feel proud of. So what is a deep neural network? You've seen this picture for logistic regression, and you've also seen neural networks with a single hidden layer. So here's an example of a neural network with 2 hidden layers and a neural network with 5 hidden layers. We say that logistic regression is a very shallow model, whereas this model here is a much deeper model. And shallow versus depth is a matter of degree. So a neural network with a single hidden layer, this would be a 2-layer neural network. Remember, when we count layers in a neural network, we don't count the input layer, we just count the hidden layers as well as the output layer. So this would be a 2-layer neural network, is still quite shallow, but not as shallow as logistic regression. Technically, logistic regression is a 1-layer neural network. But over the last several years, the AI and the machine learning community has realized that there are functions that very deep neural networks can learn that shallower models are often unable to. Although for any given problem, it might be hard to predict in advance exactly how deep a neural network you would want, so it would be reasonable to try logistic regression, try 1 and then 2 hidden layers, and view the number of hidden layers as another hyperparameter that you could try a variety of values of and evaluate on whole-data cross-validation data or on your development set. Say more about that later as well. Let's now go through the notation we'll use to describe deep neural networks. Here is a 1, 2, 3, 4-layer neural network with 3 hidden layers, and the number of units in these hidden layers are, I guess, 5, 5, 3, and then there's 1 output unit. So the notation we're going to use is going to use capital L to denote the number of layers in the network. So in this case, L is equal to 4. And so that's the number of layers And we're going to use n superscript L to denote the number of nodes or the number of units in layer lowercase l. So if we index this, the input, as layer 0, this is layer 1, this is layer 2, this is layer 3, and this is layer 4, then we have that, for example, n1, that would be this, the first hidden layer, would be equal to 5 because we have 5 hidden units there. For this one, we have that n2, the number of units in the second hidden layer, is also equal to 5. N3 is equal to 3, and N4, which is N capital L, is the number of units, is the number of output units is equal to 1, because here capital L is equal to 4. And we're also going to have here that for the input layer, N0 is just equal to Nx is equal to 3. Okay, so that's the notation we'll use to describe the number of nodes we have in different layers. For each layer L, we're also going to use AL to denote the activations in layer L. So we'll see later that in forward propagation, you end up computing AL as the activation G applied to ZL, and perhaps the activation is indexed by the layer L as well. And then we'll use WL to denote, the weights for computing the values ZL in layer L. And similarly, BL is used to compute ZL. Finally, just to wrap up on the notation, the input features are called X, but X is also the activations of layer 0. So A0 is equal to X, and the activation of the final layer, A capital L, is equal to Y hat. So A superscript square bracket capital L is equal to the predicted output, the prediction Y hat of the neural network. So you now know what a deep neural network looks like, as was the notation we'll use to describe and to compute with deep networks. I know we've introduced a lot of notation in this video, but if you ever forget what some symbol means, we've also posted on the course website a notation sheet or notation guide that you can use to look up what these different symbols means. Next, I'd like to describe what forward propagation in this type of network looks like. Let's go on to the next video. In the last video, we described what is a deep L-layer neural network and also talked about the notation we'll use to describe such networks. In this video, you'll see how you can perform forward propagation in a deep network. As usual, let's first go over what forward propagation will look like for a single training example X, and then later on we'll talk about the vectorized version where you want to carry out forward propagation on the entire training set at the same time. But given a single training example X, here's how you compute the activations of the first layer. So for this first layer, you would compute Z1 equals W1 times X plus B1. So W1 and B1 are the parameters that affect the activations in layer 1, right? Remember, this is layer 1 of the neural network. And then you compute the activations for that layer to be equal to G of Z1. And if the activation function G depends on what layer you're at, then maybe we'll index that as the activation function for layer 1. So if you do that, you've now computed the activations for layer 1. How about layer 2? Say that layer. Well, you would then compute Z2 equals W2 A1 plus B2. And then, so the activation of layer 2 is the weight matrix times the output of layer 1, so it's that value, plus the bias vector for layer 2. And then A2 equals the activation function applied to Z2. Okay? So that's it for layer 2, and so on and so forth, until you get to the output layer, that's layer 4, where you would have that Z4 is equal to the parameters for that layer times the activations from the previous layer plus that bias vector, and then similarly A4 equals G of Z4. And so that's how you compute your estimated output y hat. So just one thing to notice, x here is also equal to A0 because the input feature vector x is also the activations of layer 0. So we scratch out x. I'm going to cross out x and put A0 here. Then, all of these equations basically look the same, right? The general rule is that ZL is equal to WL times A of L minus 1 plus BL, there's a 1 there, and then the activations for that layer is the activation function applied to the values Z. So that's the general forward propagation equation. So we've done all this for a single training example. How about for doing it in a vectorized way for the whole training set at the same time? The equations look quite similar as before. For the first layer, you would have capital Z1 equals W1 times capital X plus B1, and then A1 equals G of Z1, right? And bearing in mind that X is equal to A0, these are just, the training examples stacked in different columns. You could take this, let me scratch out X, you can put A0 there. And then for the next layer, it looks similar, Z2 equals W2 A1 plus B2, and A2 equals G of Z2, right? We're just taking these vectors Z or A and so on and stacking them up. This is Z vector for the first training example, Z vector for the second training example, and so on down to the nth training example, and stacking these in columns and calling this capital Z, right? And similarly for capital A, just as capital X, all the training examples are column vectors stacked left to right. And then at the end of this process, you end up with y hat, which is equal to G of Z4. Oh, this is also equal to A4. And that's the predictions on all of your training examples stacked horizontally. So just to summarize, our notation, I'm going to modify this up here. Our notation allows us to replace lowercase z and a with the uppercase counterparts, because that already looks like a capital Z. And that gives you the vectorized version of forward propagation that you carry out on the entire training set at a time, where A0 is X. Now, if you look at this implementation of vectorization, it looks like that there is going to be a for loop here, right? So it's left for L equals 1 to 4, or for L equals 1 through capital L, that you have to compute the activations for layer 1, then for layer 2, then for layer 3, and then for layer 4. So it seems that there is a for loop here. And I know that when implementing neural networks, we usually want to get rid of explicit for loops, but this is one place where I don't think there's any way to implement this without an explicit for loop. So when implementing forward propagation, it is perfectly okay to have a for loop that computes the activations for layer 1, then layer 2, then layer 3, then layer 4. No one knows, and I don't think there exists any way to do this without a for loop that goes from 1 to capital L, from 1 through the total number of layers in the neural network. So in this place, it's perfectly okay to have an explicit for loop. So that's it for the notation for deep neural networks, as well as how to do forward propagation in these networks. If the pieces we've seen so far looks a little bit familiar to you, that's because what we've seen is taking a piece very similar to what you've seen in the neural network with a single hidden layer and just repeating that more times. Now, it turns out that when you implement a deep neural network, one of the ways to increase your odds of having a bug-free implementation is to think very systematically and carefully about the matrix dimensions you're working with. So when I'm trying to debug my own code, I'll often pull a piece of paper and just think carefully through some of the dimensions of the matrix I'm working with. Let's see how you could do that in the next video. When implementing a deep neural network, one of the debugging tools I often use to check the correctness of my code is to pull a piece of paper and just work through the dimensions of the matrix I'm working with. So let me show you how to do that, since I hope this will make it easier for you to implement your deep nets as well. So capital L is equal to 5. Right? Count down quickly, not counting the input layer. There are 5 layers here, so 4 hidden layers and 1 output layer. And so if you implement forward propagation, the first step will be Z1 equals W1 times the input features X plus B1. So let's ignore the bias terms B for now and focus on the parameters W. Now this first hidden layer has 3 hidden units. So this is layer 0, layer 1, layer 2, layer 3, layer 4, and layer 5. So using the notation we had from the previous video, we have that N1, which is the number of hidden units in layer 1, is equal to 3. And here we would have that N2 is equal to 5, N3 is equal to 4, N4 is equal to 2, and N5 is equal to 1. And so far we've only seen neural networks with a single output unit, but later, in later courses, we'll talk about neural networks with multiple output units as well. And finally, for the input layer, we also have N0 equals Nx is equal to 2. So now let's think about the dimensions of Z, W, and X. Z is the vector of activations for this first hidden layer. So Z is going to be 3 by 1. It's going to be a 3-dimensional vector. So I'm going to write it as a n1 by 1 dimensional vector, or n1 by 1 dimensional matrix. Right? It's 3 by 1 in this case. Now, how about the input features X? X, we have 2 input features. So X is, in this example, 2 by 1. But more generally, it will be n0 by 1. So what we need is for the matrix W1 to be something that when we multiply an n0 by 1 vector to it, we get an n1 by 1 vector, right? So you have sort of a 3-dimensional vector equals something times a 2-dimensional vector. And so by the rules of matrix multiplication, this has got to be a 3 by 2 matrix. Right? Because a 3 by 2 matrix times a 2 by 1 matrix, or times a 2 by 1 vector, that gives you a 3 by 1 vector. And more generally, this is going to be an n1 by n0 dimensional matrix. So what we figured out here is that the dimensions of W1 has to be n1 by n0. And more generally, the dimensions of WL must be NL by NL minus 1. So for example, the dimensions of W2, for this, it will have to be 5 by 3, or it will be N2 by N1, because we're going to compute Z2 as W2 times A1, and again, let's ignore the bias for now. But so this is going to be 3 by 1, and we need this to be 5 by 1, and so this had better be 5 by 3. And similarly, W3 is really the dimension of the next layer, comma, the dimension of the previous layer. So this is going to be 4 by 5. W4 is going to be 2 by 4, and W5 is going to be 1 by 2. Okay? So the general formula to check is that when you're implementing the matrix for layer L, that the dimension of that matrix be NL by N L minus 1. Now, let's think about the dimension of this vector b. This is going to be a 3 by 1 vector, so you have to add that to another 3 by 1 vector in order to get a 3 by 1 vector as the output. Or in this example, you need to add this, which is going to be 5 by 1, so it's going to be another 5 by 1 vector in order for the sum of these two things that I have in the boxes to be itself a 5 by 1 vector. So the more general rule is that in the example on the left, b1 is n1 by 1, right? That's 3 by 1. And in the second example, it is this is n2 by 1. And so the more general case is that BL should be NL by 1 dimensional. So hopefully these two equations help you to double check that the dimensions of your matrices W as well as of your vectors B are the correct dimensions. And of course, if you're implementing backpropagation, then the dimensions of dW should be the same as the dimension of W. So dW should be the same dimension as W, and dB should be the same dimension as B. Now, the other key set of quantities whose dimensions to check are these Z, X, as well as A of L, which we didn't talk too much about here, but because Z of L is equal to G of A of L applied element-wise, then Z and A should have the same dimension in these types of networks. Now, let's see what happens when you have a vectorized implementation that looks at multiple examples at a time. Even for a vectorized implementation, of course, the dimensions of W, B, dW, and dB will stay the same, but the dimensions of Z, A, as well as X will change a bit in your vectorized implementation. So previously, we had Z1 equals W1 times X plus B1, where this was N1 by 1, this was N1 by N0, X was N0 by 1, and B was N1 by 1. Now, in a vectorized implementation, you would have Z1 equals W1 times X plus B1, where now Z1 is obtained by taking the Z1s for the individual examples, so that's Z11, Z12, up to Z1M, and stacking them as follows, and this gives you Z1. So the dimension of Z1 is that instead of being N1 by 1, it ends up being N1 by M, if M is the size of your training set. The dimensions of W1 stays the same, so it's still N1 by N0. And X, instead of being N0 by 1, is now all your training examples stacked horizontally. So it's now N0 by M. And so you notice that when you take a N1 by N0 matrix and multiply that by an N0 by M matrix, that together they actually give you an N1 by M dimensional matrix as expected. Now the final detail is that B1 is still N1 by 1, but when you take this and add it to B, then through Python broadcasting, this will get duplicated into an N1 by M matrix and then added element-wise. So on the previous slide, we talked about the dimensions of W, B, dW, and dB. Here, what we see is that whereas ZL, as well as AL, are of dimension NL by 1, we have now instead that capital ZL, as well as capital AL, are NL by M. And a special case of this is when L is equal to 0, in which case A0 which is equal to just your training set input features x, is going to be equal to n0 by m, as expected. And of course, when you're implementing this in backpropagation, we'll see later you end up computing dz as well as dA, and so these will of course have the same dimension as z and a. So I hope the little exercise went through helps clarify the dimensions of the various matrices you'll be working with. When you implement backpropagation for a deep neural network, so long as you work through your code and make sure that all the matrices dimensions are consistent, that will usually help go some ways toward eliminating some class of possible bugs. So I hope that exercise for figuring out the dimensions of the various matrices you'll be working with is helpful. When you implement a deep neural network, if you keep straight the dimensions of these various matrices and vectors you're working with, hopefully that'll help you eliminate some class of possible bugs. It certainly helps me get my code right. So next, we've now seen some of the mechanics of how to do certainly forward propagation in a neural network. But why are deep neural networks so effective, and why do they do better than shallow representations? Let's spend a few minutes in the next video to discuss. We've all been hearing that deep neural networks work really well for a lot of problems. It's not just that they need to be big neural networks, it's that specifically they need to be deep or to have a lot of hidden layers. So why is that? Let's go for a couple examples and try to gain some intuition for why deep networks might work well. So first, what is a deep network computing? If you're building a system for face recognition or face detection, here's what a deep neural network could be doing. Perhaps you input a picture of a face. Then the first layer of the neural network you can think of as maybe being a feature detector or an edge detector. In this example, I'm plotting what a neural network with maybe 20 hidden units might be trying to compute on this image, with the 20 hidden units visualized by these little square boxes. So for example, this little visualization represents a hidden unit that's trying to figure out if, where are the edges of that orientation in the image. And maybe this hidden unit might be trying to figure out where are the horizontal edges in this image. And when we talk about convolutional networks in a later course, this particular visualization will make a bit more sense. But informally, you can think of the first layer of the neural network as looking at a picture and trying to figure out where are the edges in this picture. Now that it's figured out where are the edges in this picture by grouping together pixels to form edges, it can then take the detected edges and group edges together to form parts of faces. So for example, you might have a little neuron trying to see if it's finding an eye, or a different neuron trying to find that part of the nose. And so by putting together lots of edges, it can start to detect different parts of faces. And then finally, by putting together different parts of faces, like an eye or a nose or an ear or a chin, it can then try to recognize or detect different types of faces. So intuitively, you can think of the earlier layers of a neural network as detecting simpler functions like edges, and then composing them together in the later layers of a neural network so that it can learn more and more complex functions. These visualizations will make more sense when we talk about convolutional nets. And one technical detail of this visualization, the edge detectors are looking in relatively small areas of an image, maybe very small regions like that. And then the facial detectors, can look at maybe much larger areas of the image. But the main intuition when you take away from this is just finding simpler things like edges and then building them up, composing them together to detect more complex things like an eye or a nose, and then composing those together to find even more complex things. And this type of simple to complex hierarchical representation or compositional representation applies in other types of data than images and face recognition as well. For example, if you're trying to build a speech recognition system, it's hard to visualize speech, but if you input an audio clip, then maybe the first level of a neural network might learn to detect low-level audio waveform features, such as, is this tone going up, is it going down, is it white noise or sibilant sound like s, right? And what is the pitch, but it can detect low-level waveform features like that. And then by composing low-level waveforms, maybe you'll learn to detect basic units of sound. So in linguistics, they're called phonemes. But for example, in the word cat, the k is a phoneme, the a is a phoneme, the t is another phoneme, but it learns to find maybe the basic units of sound. And then composing that together, maybe you learn to recognize words in the audio, and then maybe you can compose those together in order to recognize entire, phrases or sentences. So a deep neural network with multiple hidden layers might be able to have the earlier layers learn these lower level simpler features, and then have the later deeper layers then put together the simpler things as detected in order to detect more complex things, like recognize specific words or even phrases or sentences that you're uttering in order to carry out speech recognition. And what we see is that whereas the earlier layers are computing what seems like relatively simple functions of the input, such as where are the edges, by the time you get deep in the network, you can actually do, surprisingly complex things, such as detect faces or detect words or phrases or sentences. Some people like to make an analogy between deep neural networks and the human brain, where we believe, or neuroscientists believe, that the human brain also starts off detecting simple things like edges in what your eyes see, and then builds those up to detect more complex things like the faces that you see. I think analogies between deep learning and the human brain are sometimes a little bit dangerous, but there is a lot of truth to this being how we think the human brain works, and that the human brain probably detects simple things like edges first and then puts them together to form more and more complex objects. And so that has served as a loose form of inspiration for some deep learning as well. We'll say a bit more about the human brain, or about the biological brain, in a later video this week. The other piece of intuition about why deep networks seem to work well is the following. So this result comes from circuit theory, which pertains to thinking about what types of functions you can compute with different AND gates and OR gates and NOT gates, basically logic gates. So informally, they're functions you compute with a relatively small but deep neural network. And by small, I mean the number of hidden units is relatively small. But that if you try to compute the same function with a shallow network, so if you aren't allowed enough hidden layers, then you might require exponentially more hidden units to compute. So let me just give you one example and illustrate this a bit informally. But let's say you're trying to compute the exclusive OR, or the parity of all your input features. So you're trying to compute x1, x4, x2, x4, x3, x4 up to xn, if you have n or nx features. So if you build an XOR tree like this, right? So first compute the XOR of x1 and x2, then take x3 and x4 and compute their XOR. And technically, if you're just using AND, OR, and NOT gate, you might need a couple layers to compute the XOR function rather than just one layer. But with a relatively small circuit, you can compute the XOR, right? And so on. And then you can build really an XOR tree like so, until eventually you have a circuit here that outputs, let's call this y, that outputs y hat equals y, the exclusive OR, or the parity of all of these input bits. So to compute the XOR, the depth of the network will be on the order of log n, right, with this type of XOR tree. So the number of nodes, or the number of circuit components, or the number of gates in this network is not that large. You don't need that many gates in order to compute the exclusive OR. But now, if you're not allowed to use a neural network with multiple hidden layers, with, in this case, order log n hidden layers, if you're forced to compute this function with just one hidden layer, right? So you have all these things going into, set of hidden units, and then these things then outputs y. Then in order to compute the parity of or to compute this XOR function, this hidden layer will need to be exponentially large, because essentially you need to exhaustively enumerate all 2 to the n possible configurations, or on the order of 2 to the n possible configurations of the input bits that result in the exclusive OR being either 1 or 0. So you end up needing a hidden layer that is exponentially large in the number of bits. I think technically you could do this with 2 to the n minus 1 hidden units, right? But that's the order 2 to the n. So it's going to be exponentially large in the number of bits. So I hope this gives a sense that there are mathematical functions that are much easier to compute with deep networks than with shallow networks. I have to admit, I personally found the result from circuit theory less useful for gaining intuitions, but this is one of the results that people often cite when explaining the value of having very deep representations. Now, in addition to these reasons for preferring deep neural networks, to be perfectly honest, I think the other reason the term deep learning has taken off is just branding, right? These things used to be called neural networks with a lot of hidden layers, but the phrase deep learning, you know, is just a great brand. It just is so deep, right? So I think that once that term caught on, that really neural networks rebranded, or neural networks with many hidden layers rebranded, helped to capture the popular imagination as well. But regardless of the PR branding, deep networks do work well. Sometimes people go overboard and insist on using tons of hidden layers, but when I'm starting out with a new problem, I'll often really start out with even logistic regression, then try something with 1 or 2 hidden layers and use that as a hyperparameter, use that as a parameter or hyperparameter that you tune in order to try to find the right depth for your neural network. But over the last several years, there has been a trend toward people finding that for some applications, very, very deep neural networks, you know, with maybe many dozens of layers sometimes, can sometimes be the best model for a problem. So that's it for the intuitions for why deep learning seems to work well. Let's now take a look at the mechanics of how to implement not just forward propagation, but also back propagation. In the earlier videos from this week, as well as from the videos from the past several weeks, you've already seen the basic building blocks of forward propagation and back propagation, the key components you need to implement a deep neural network. Let's see how you can put these components together to build your deep net. Here's a network with a few layers. Let's pick one layer and look at the computations focusing on just that layer for now. So for layer L, you have some parameters WL and BL. And for the forward prop, you will input deactivations A, L-1 from the previous layer, and output AL. So the way we did this previously was you compute ZL equals WL times AL-1 plus BL, and then AL equals G of ZL, right? So that's how you go from the input AL-1 to the output AL. And it turns out that for later use, it'll be useful to also cache the value ZL. So let me include this cache as well, because storing the value ZL will be useful for for the back propagation step later. And then for the backward step, or really for the back propagation step, again focusing on the computation for this layer L, you're going to implement a function that inputs dA of L and outputs dA L-1. And just to flesh out the details, the input is actually dA of L as well as the cache. So you have available to you the value of ZL that you computed. And then in addition to outputting dAL-1, you will output the gradients you want in order to implement gradient descent for learning. Okay, so this is the basic structure of how you implement this forward step. We're going to call it a forward function, as well as this backward step, which we're going to call a backward function. So just to summarize, in layer L, you're going to have the forward step, or the forward prop, or the forward function, input AL-1 and output AL. And in order to make this computation, you need to use WL and BL. And it'll also output a cache, which contains ZL. Right? And then the backward function used in the backprop step will be another function that now inputs dA of L and outputs dA L minus 1. So it tells you, given the derivatives with respect to these activations, that's dA of L, what are the derivatives, or how much do I wish AL minus 1 changes? So compute the derivatives with respect to deactivations from the previous layer. Within this box, right, you need to use WL and BL. And it turns out along the way, you end up computing DZL. And then this box, this backward function, can also output DWL and DBL. And I was sometimes using red arrows to denote the backward iteration. So if you prefer, we could draw these arrows in red. So if you can implement these two functions, then the basic computation of the neural network will be as follows. You're going to take the input features A0, feed that in, and that will compute the activations of the first layer. Let's call that A1. And to do that, you needed W1 and B1. And then we'll also, cache away Z1. Right? Now, having done that, you feed that to the second layer, and then using W2 and B2, you're going to compute the activations of the next layer, A2, and so on, until eventually you end up outputting A capital L, which is equal to Y hat. And along the way, we cached all of these values Z. So that's the forward propagation step. Now, for the back propagation step, what we're going to do will be a backward sequence of iterations in which you are going backward and computing gradients like so. So we're actually going to feed in here dA of L, and then this box will give us dA of L minus 1, and so on until we get dA 2, dA 1. You could actually get one more output to compute dA 0, but this is the derivative with respect to your input features, which is not useful, at least for training the weights of these supervised neural networks. So you could just stop it there. But along the way, backprop also ends up outputting DWL, DBL, right? Just use the parameters WL and BL. This would output DW3, DB3, and so on. So you end up computing all the derivatives you need. And so just to maybe fill in the structure of this a little bit more, right? These boxes will use those parameters as well. WL, BL. And it turns out that we'll see later that inside these boxes we'll end up computing DZs as well. So one iteration of training for a neural network involves starting with A0, which is X, and going through forward prop as follows, computing Y hat, and then using that to compute this, and then back prop, right, doing that. And now you have all these derivative terms. And so, W will get updated as W minus the learning rate times DW, right, for each of the layers. And similarly, for B, right? Now that you've computed backprop and have all these derivatives. So that's one iteration of gradient descent for your neural network. Now, before moving on, just one more implementational detail. Conceptually, it'll be useful to think of the cache here as storing the value of Z for the backward functions. But when you implement this, and you see this in the programming exercise, when you implement this, you find that the cache may be a convenient way to get this value of the parameters of W1, B1 into the backward function as well. So in the programming exercise, you actually store in the cache z as well as w and b, right? So to store z2, w2, b2. But from an implementational standpoint, I just find this a convenient way to just get the parameters copied to where you need to use them later when you're computing backpropagation. So that's just an implementational detail that you see when you do the programming exercise. So you've now seen what are the basic building blocks for implementing a deep neural network. In each layer, there's a forward propagation step, and there's a corresponding backward propagation step, and there's a cache to pass information from one to the other. In the next video, we'll talk about how you can actually implement these building blocks. Let's go on to the next video. In the previous video, you saw the basic blocks of implementing a deep neural network, a forward propagation step for each layer and a corresponding backward propagation step. Let's see how you can actually implement these steps. We'll start with forward propagation. Recall that what this will do is input AL-1 and output AL and the cache ZL. And we just said that from implementational point of view, maybe we'll cache WL and BL as well, just to make the functions call a bit easier in the programming exercise. And so the equations for this should already look familiar. The way to implement a forward function is just this, equals WL times AL minus 1 plus BL, and then AL equals the activation function applied to Z. And if you want a vectorized implementation, then it's just that times a l minus 1 plus b, with the b, adding b being Python broadcasting, and al equals g applied element-wise to z. And you remember on the diagram for the forward step, right, we had this chain of boxes going forward. So you initialize that with feeding in a0, which is equal to x. So you initialize this. Really, what is the input to the first one, right? It's really a0, which is the input features to either for one training example if you're doing one example at a time, or a capital 0, the entire training set if you are processing the entire training set at a time. So that's the input to the first forward function in the chain, and then just repeating this allows you to compute forward propagation from left to right. Next, let's talk about the backward propagation step. Here, your goal is to input DAL and output DAL minus 1 and DWL and DB. Let me just write out the steps you need to compute these things. DZL is equal to DAL, element-wise product with G of L prime Z of L. And then to compute the derivatives, dWL equals dzL times A of L minus 1. I didn't explicitly put that in the cache, but it turns out you need this as well. And then dBL is equal to dzL. And finally, dA of L minus 1 is equal to WL transpose times DZL. Okay, and I don't want to go through the detailed derivation for this, but it turns out that if you take this definition for dA and plug it in here, then you get the same formula as we had in the previous week for how you compute DZL as a function of the previous DZL. In fact, well, if I just plug that in here, you end up that DZL is equal to WL plus 1 transpose dz L plus 1 times GL prime Z of L. I know this is looks like a lot of algebra. You could actually double check for yourself that this is the equation we had written down for backpropagation last week when we were doing a neural network with just a single hidden layer. And as a reminder, this times this element-wise product, but so all you need is those four equations to implement your backward function. And then finally, I'll just write out the vectorized version. So the first line becomes dzL equals dAL element-wise product with GL prime of ZL maybe no surprise there. dWL becomes 1 over m dzL times A L minus 1 transpose. And then dBL becomes 1 over m np dot sum dzL, and then x is equals 1. Keep dims equals true. We talked about the use of np.sum in the previous week to compute dB. And then finally, dA, L minus 1, is WL transpose times dZ of L. So this allows you to input this quantity, dA, over here, and output dWL, dBL, the derivatives you need, as well as dA L minus 1, right, as follows. So that's how you implement the backward function. So just to summarize, take the input x. You might have the first layer, maybe has a ReLU activation function, then go to the second layer, maybe uses another ReLU activation function, goes to the third layer, maybe has a sigmoid activation function if you're doing binary classification, and this outputs y hat. And then, using y hat, you can compute the loss. And this allows you to start your backward iteration. I'll draw the arrows first, I guess, so I don't have to change pens too much. Where you would then have backprop compute the derivatives, compute dW3, dB3, dW2, dB2, dW1, dB1, and along the way you would be computing, I guess the cache would transfer Z1, Z2, Z3, and here you pass back with dA2 and dA1. This could compute dA0, but we won't use that, so you can just discard that, right? And so this is how you implement forward prop and back prop for a 3-layer neural network. Now, there's just one last detail that I didn't talk about, which is for the forward recursion, we would initialize it with the input data x. How about the backward recursion? Well, it turns out that dA of L, when you're using logistic regression, when you're doing binary classification, is equal to y over a plus 1 minus y over 1 minus a. So it turns out that the derivative of the loss function with respect to the output, with respect to y hat, can be shown to be equal to this. If you're familiar with calculus, if you look up the loss function L and take derivatives with respect to y hat or respect to a, you could show that you get that formula. So this is the formula you should use for dA for the final layer, capital L. And of course, if you were to have a vectorized implementation, then you initialize the backward recursion, not with this, but with dA, capital A, for the layer L, which is going to be, the same thing for the different examples, right, over A for the first training example plus 1 minus y for the first training example over 1 minus a for the first training example, dot, 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 down to the mth training example. It's 1 minus a of m. So that's how you implement the vectorized version. That's how you initialize the vectorized version of backpropagation. So you've now seen the basic building blocks of both forward propagation as well as backpropagation. Now, if you implement these equations, you will get a correct implementation of forward prop and back prop to get you the derivatives you need. You might be thinking, wow, that was a lot of equations and I'm slightly confused. I'm not quite sure I see how this works. And if you're feeling that way, my advice is when you get to this week's programming assignment, you will be able to implement these for yourself and they'll be much more concrete. And I know there was a lot of equations and maybe some of the equations didn't make complete sense, but if you work through the calculus and the linear algebra, which is not easy. So, feel free to try, but that's actually one of the more difficult derivations in machine learning. It turns out the equations we wrote down are just the calculus equations for computing the derivatives, especially in backprop. But once again, if this feels a little bit abstract, a little bit mysterious to you, my advice is when you've done the programming exercise, it will feel a bit more concrete to you. Although I have to say, even today, when I implement a learning algorithm, sometimes even I'm surprised when my learning algorithm implementation works. And it's because a lot of the complexity of machine learning comes from the data rather than from the lines of code. So sometimes you feel like you implement a few lines of code, not quite sure what it did, but this almost magically works. And it's because a lot of the magic is actually not in the piece of code you write, which is often, not too long. It's not exactly simple, but it's not, 10,000 or 100,000 lines of code, but you feed it so much data that sometimes, even though I've worked in machine learning for a long time, sometimes it still, surprises me a bit when my learning algorithm works, because a lot of the complexity of your learning algorithm comes from the data rather than necessarily from your writing, thousands and thousands of lines of code. All right, so that's how you implement deep neural networks. And again, this will become more concrete when you've done the programming exercise. Before moving on, I want to discuss, in the next video, hyperparameters and parameters. It turns out that when you're training deep nets, being able to organize your hyperparameters well will help you be more efficient in developing neural networks. In the next video, let's talk about exactly what that means. Being effective in developing your deep neural nets requires that you not only organize your parameters well, but also your hyperparameters. So what are hyperparameters? Let's take a look. So the parameters of your model are W and B. And there are other things you need to tell your learning algorithm, such as the learning rate alpha, because you need to set alpha, and that in turn will determine how your parameters evolve, or maybe the number of iterations of gradient descent you carry out. Your learning algorithm has other numbers that you need to set, such as the number of hidden layers, so we call that capital L, or the number of hidden units, right, such as N1, N2, and so on. And then you also have the choice of activation function. Do you want to use a ReLU or a tanh or a sigmoid or something, especially in the hidden layers? And so all of these things are things that you need to tell your learning algorithm. And so these are parameters that control the ultimate parameters W and B. And so we call all of these things below hyperparameters. Because these things like alpha, the learning rate, the number of iterations, number of hidden layers, and so on, these are all parameters that control W and B. So we call these things hyperparameters. Because it is the hyperparameters that somehow determine the final value of the parameters W and B that you end up with. In fact, deep learning has a lot of different hyperparameters. Later, in the later course, we'll see other hyperparameters as well, such as the momentum term, the mini batch size, various forms of regularization parameters, and so on. And if none of these terms at the bottom make sense yet, don't worry about it. We'll talk about them in the second course. Because deep learning has so many hyperparameters, in contrast to earlier eras of machine learning, I'm going to try to be very consistent in calling the learning rate alpha a hyperparameter rather than calling it a parameter. I think in earlier eras of machine learning, when we didn't have so many hyperparameters, most of us used to be a bit sloppier and just call alpha a parameter. And technically, alpha is a parameter, but it's a parameter that determines the real parameters. So I've tried to be consistent in calling these things like alpha, the number of iterations, and so on, hyperparameters. So when you're training a deep net for your own application, you find that there may be a lot of possible settings for the hyperparameters that you need to just try out. So applied deep learning today is a very empirical process where often you might have an idea. For example, you might have an idea for the best value for the learning rate. You might say, well, maybe alpha equals 0.01. I want to try that. then you implement it, try it out, and then see how that works. And then based on that outcome, you might say, you know what, I've changed my mind. I want to increase the learning rate to 0.05. And so if you're not sure what's the best value for the learning rate to use, you might try one value of the learning rate alpha and see the cost function j go down like this. Then you might try a larger value for the learning rate alpha and see the cost function blow up and diverge. Then you might try another version and see it go down really fast but converge to a higher value. And you might try another version and see it, see the cost function j do that. Then after trying a set of values, you might say, okay, it looks like the value of alpha gives me a pretty fast learning and allows me to converge to a lower cost function j, so I'm going to use this value of alpha. You saw in the previous slide that there are a lot of different hyperparameters, and it turns out that when you're starting on a new application, I actually find it very difficult to know in advance exactly what's the best value of the hyperparameters. So what will often happen is you just have to try out many different values and go around this cycle. Try out some value. Maybe you try 5 hidden layers with this many number of hidden units, implement that, see if it works, and then iterate. So the title of the slide is that applied deep learning is a very empirical process. An empirical process is maybe a fancy way of saying you just have to try out a lot of things and see what works. Another effect I've seen is that deep learning today is applied to so many problems ranging from computer vision to speech recognition to natural language processing to a lot of structured data applications such as maybe online advertising or web search or product recommendations and so on. And what I've seen is that first, I've seen researchers from one discipline, any one of these, try to go to a different one, and sometimes the intuitions about hyperparameters carries over, and sometimes it doesn't. So I often advise people, especially when we're starting on a new problem, to just try out a range of values and see what works. And in the next course, we'll see a systematic way. We'll see some systematic ways for trying out a range of values. Right. And second, even if you're working on one application for a long time, maybe you're working on online advertising, as you make progress on the problem, it's quite possible that the best value for the learning rate, the number of hidden units and so on might change. So even if you've tuned your system to have the best value of hyperparameters today, it's possible you find that the best value might change a year from now. Maybe because the compute infrastructure, be it CPUs or the type of GPU you're running on or something has changed. But so maybe one rule of thumb is, every now and then, maybe every few months if you're working on a problem for an extended period of time, for many years, just try a few values for the hyperparameters and double check if there's a better value for the hyperparameters. And as you do so, you slowly gain intuition as well about the hyperparameters that work best for your problem. And I know that this might seem like an unsatisfying part of deep learning, that you just have to try a lot of values for these hyperparameters, but maybe this is one area where deep learning research is still advancing, and maybe over time we'll be able to give better guidance for the best hyperparameters to use. But it's also possible that because CPUs and GPUs and networks and data sets are all changing, and it's possible that the guidance won't converge for some time, and you just need to keep trying out different values and evaluate them on a Hodder-Krauss validation set or something, and pick the value that works for your problem. So that was a brief discussion of hyperparameters. In the second course, we'll also give some suggestions for how to systematically explore the space of hyperparameters. But by now, you actually have pretty much all the tools you need to do the programming exercise. Before you do that, just want to share with you one more set of ideas, which is I often am asked, what does deep learning have to do with the human brain? So what does deep learning have to do with the brain? At the risk of giving away the punchline, I would say not a whole lot. But let's take a quick look at why people keep making the analogy between deep learning and the human brain. When you implement a neural network, this is what you do, forward prop and back prop. And I think because it's been difficult to convey intuitions about what these equations are doing, really gradient descent on a very complex function, the analogy that is like the brain has become really an oversimplified explanation for what this is doing. But the simplicity of this makes it, kind of seductive for people to just say it publicly, as well as for media to report it, and it's certainly caught the popular imagination. And there is a very loose analogy between, let's say, a logistic regression unit with a sigmoid activation function, and here's a cartoon of a single neuron in the brain. In this picture of a biological neuron, this neuron, which is a cell in your brain, receives electric signals from other neurons, maybe X1, X2, X3, or maybe from other neurons, A1, A2, A3, does a simple thresholded computation, and then if this neuron fires, it sends a pulse of electricity down the axon, down this long wire, perhaps to other neurons. So there is a very simplistic analogy between a single logistic unit, between a single neuron in a neural network and a biological neuron like that shown on the right. But I think that today, even neuroscientists have almost no idea what even a single neuron is doing. A single neuron appears to be much more complex than we are able to characterize with neuroscience. And while some of what it's doing is a little bit like logistic regression, there's still a lot about what even a single neuron does that no human today understands. For example, exactly how neurons in the human brain learns is still a very mysterious process. And it's completely unclear today whether the human brain uses an algorithm that's anything like backpropagation or gradient descent, or if there's some fundamentally different learning principle that the human brain uses. So when I think of deep learning, I think of it as being very good at learning very flexible functions, very complex functions, to learn X to Y mappings, to learn input-output mappings in supervised learning. And whereas the is like the brain analogy, maybe that was useful once, I think the field has moved to the point where that analogy is breaking down, and I tend not to use that analogy much anymore. So that's it for neural networks and their brain. I do think that maybe the field of computer vision has taken a bit more inspiration from the human brain than other disciplines that also apply deep learning, but I personally use the analogy to the human brain less than I used to. So that's it for this video. You now know how to implement forward prop and back prop and gradient descent even for deep neural networks. Best of luck with the primary exercise, and I look forward to sharing more of these ideas with you in the second course.